Look up at the night sky on a clear, dark evening. Each of those points of light is a sun, many with worlds of their own, and the vast blackness between them isn't empty. It's a deep, mysterious canvas holding the universe's greatest secrets. This is where our ultimate quest begins, a journey into the heart of cosmic riddles and hidden dimensions that have captivated and confounded the greatest minds for generations. The cosmos presents itself as an infinite, silent library, but here's the astonishing part. Most of its books are written in invisible ink. We can sense their presence, we can see the shadow they cast on the shelves of reality, but the words themselves, the fundamental truths about dark matter, the nature of time, the very fabric of space, remain just out of reach, waiting for us to find the right light to read them. This isn't a passive observation. It's an active, thrilling invitation to decipher what lies beyond our ordinary senses, to explore realms that could completely redefine our understanding of everything. Why does this profound search matter so much right now to us? It's because this isn't merely an academic exercise for scientists in distant laboratories. Unraveling these cosmic mysteries is fundamentally about understanding our own place in this vast expanse. It's about the technologies we might unlock, the new physics that could revolutionize our world, and the humbling, awe-inspiring realization that we are part of a story far grander than we ever imagined. So let me ask you a question that might linger in your mind long after this video ends. What if the reality we experience every single day, the solid ground beneath your feet, the air you breathe, the stars you see, is only a tiny fraction of what actually exists? What if there are more dimensions hidden from our view that influence everything from the force of gravity to the very flow of time? How would discovering them change not just science, but your personal perspective on life itself? In the journey ahead, we will travel together through some of the most baffling phenomena known to science. We'll delve into the cutting-edge theories that brave physicists are proposing to explain the unexplainable, and we'll uncover the incredible tools, from colossal underground detectors to space telescopes peering back to the dawn of time, that are our only hope for probing the unknown. This is more than a documentary. It's a mind-expanding adventure designed to blend a sense of profound wonder with rigorous, insightful inquiry. Every revelation we uncover will bring us one step closer to the universe's deepest truths. So let's begin this exploration together, setting the stage for a narrative where curiosity is our compass and the cosmos is our guide. Picture an astronomer alone at their console in the dead of night, when a signal from the void floods their headphones. It isn't static or a known pulsar's steady beat. It's a sequence of pulses repeating in a rhythm that defies every equation in the book of physics. Colleagues are called in, data is scrutinized, and yet no one can explain its origin. That moment of collective, global head-scratching, that blend of excitement and utter bafflement, is the very essence of a cosmic riddle. These aren't just minor curiosities or gaps in a spreadsheet. They are fundamental cracks in the foundation of our understanding, profound questions that nature has posed and for which we have no satisfying answers. Think of the inexplicable gravitational tug we call dark matter, which sculpts galaxies yet remains completely invisible, or the universe's accelerating expansion, driven by a mysterious dark energy that seems to be pushing the cosmos apart at an ever-increasing rate. Each of these puzzles challenges the core principles we thought were settled, forcing us to reconsider the very rules that govern reality. As the renowned physicist Brian Greene so aptly put it, the universe is a puzzle waiting to be solved, and every mystery we unravel reveals another layer of complexity. This isn't a futile endeavor, it's the engine of scientific progress. The moment we think we have it all figured out, a new cosmic riddle emerges, humbling us and propelling our curiosity forward. So, what exactly elevates a strange observation to the status of a full-blown cosmic riddle? It often boils down to a glaring inconsistency between what we see and what our theories predict. Take the Pioneer anomaly, for instance. For decades, scientists were perplexed by the tiny, unexplained deceleration acting on the Pioneer 10 and 11 spacecraft as they journeyed into the outer solar system. Our models of gravity and spacecraft dynamics couldn't account for it, suggesting some unseen force or perhaps even a subtle flaw in our understanding of physics itself was at play. While this particular mystery was eventually attributed to the subtle effect of heat radiating unevenly from the spacecraft's generators, its long reign as an unsolved riddle perfectly illustrates the nature of these challenges. Several key aspects define these profound mysteries. First is their sheer persistence. They withstand our most advanced technology and our brightest minds, remaining unsolved for years, decades, or even centuries. The famous WOW signal from 1977 is a perfect example, a powerful, narrowband radio burst that lasted 72 seconds and has never been detected again despite numerous attempts. It just sits there in the data, a silent siren call that continues to fuel debates about its origin, from a passing comet to an intentional broadcast from an alien civilization. Second, cosmic riddles hold the potential to completely rewrite the laws of physics. Cracking one open could reveal new particles, new forces, or new dimensions, fundamentally altering our textbooks. And third, they play a crucial role in inspiring new generations of thinkers and explorers. The very existence of a deep, unsolved mystery is a powerful call to adventure, inviting fresh minds to apply new perspectives. Consider the Fermi Paradox, a riddle that strikes at the heart of our cosmic loneliness. The universe is ancient and vast, with billions of planets that could potentially support life. The numbers suggest the galaxy should be teeming with civilizations, and yet when we listen, we are met with a profound and unsettling silence. As the physicist Enrico Fermi famously asked, "Where is everybody?" This paradox pushes us to question our most basic assumptions. Are we the first? Are we alone? Or are civilizations inevitably doomed to self-destruct before they can master interstellar travel? Perhaps the answer is even more strange. Maybe advanced life forms communicate in ways we haven't even thought to look for, or they exist in realms we cannot perceive. This single riddle expands our search parameters and forces us to think not just about biology or astronomy, but about sociology, technology, and the ultimate fate of intelligence itself. So, as we stand before these grand, unanswered questions, it's worth pausing to reflect on their deeper impact. How does living in a universe filled with such profound puzzles shape our perception of reality? They teach us humility, reminding us that our knowledge is still in its infancy, but they also fill us with a sense of purpose and wonder. What might we learn about the fabric of space and time if we finally decipher the riddle of dark matter? What would it reveal about our own place in the cosmos if we understood why the universe seems so fine-tuned for life? The pursuit of these answers is more than an academic exercise. It's a journey that defines our species, and this exploration of what these mysteries are naturally leads us to consider the ingenious tools, the collaborative spirit, and the bold mindsets required to even begin tackling them. In the 1930s, a brilliant and often contentious astronomer named Fritz Zwicky was studying the Coma Cluster, a vast collection of galaxies millions of light years away. He made a simple yet earth-shattering calculation. By measuring how fast these galaxies were orbiting the cluster's center, he could determine the total mass needed to hold them together with gravity. The result was staggering. The galaxies were moving so incredibly fast that the visible mass of all the stars and gas in the cluster was nowhere near enough to provide the necessary gravitational glue. The entire system should have flown apart, yet it remained intact. Zwicky concluded there must be something else there, a huge amount of unseen matter providing the extra gravity. He called this mysterious substance dunkel materie, or dark matter, and in doing so, he ignited a scientific quest that continues to this day, a century-long hunt for the universe's most abundant yet elusive ingredient. We now know that dark matter makes up roughly 27% of the entire cosmos. To put that in perspective, all the stars, planets, nebulae, and every single thing we can see with our most powerful telescopes accounts for less than 5%. Dark matter is the dominant architectural material of the universe, the invisible scaffolding upon which galaxies are built. But here is the central enigma. It does not interact with light in any way. It doesn't emit it, absorb it, or reflect it. It is completely and utterly dark to the entire electromagnetic spectrum. We cannot see it, photograph it, or scan it. Its presence is betrayed solely by its gravitational pull, a ghostly hand that guides the motion of stars and shapes the largest structures in the cosmos. Decades after Zwicky's initial insight, the astronomer Vera Rubin provided what many consider the most compelling evidence for dark matter. She meticulously mapped the rotation speeds of stars within spiral galaxies. According to Newtonian gravity, stars on the outer edges of a galaxy, far from the central bulge of mass, should orbit much more slowly than those near the center, just as Pluto orbits the Sun more slowly than Earth. But Rubin's data revealed something astonishing. The stars at the outskirts of galaxies were orbiting just as fast as those near the center. The only plausible explanation was that each galaxy was embedded within a massive, spherical halo of something invisible, dark matter, extending far beyond the visible galactic disk. This halo provides the extra gravitational force to whip those outer stars around at such high speeds. Rubin famously captured the frustration and wonder of this search when she said, "We are looking at the universe through a keyhole, and dark matter is the door we haven't opened yet." So, what exactly is this substance? Theorists have proposed several compelling candidates. One of the leading ideas is that dark matter is made of weakly interacting massive particles, or WIMP. These are hypothetical particles that are heavy, yet they interact with ordinary matter only through gravity and the weak nuclear force, making them incredibly difficult to catch. Another candidate is the action, a particle that is extremely light but theorized to exist in such vast numbers that it could account for the missing mass. There's even a more exotic possibility that dark matter consists of primordial black holes, tiny black holes formed in the intense density of the Big Bang. To test these ideas, scientists have devised incredibly sensitive experiments. Deep underground, in abandoned mines and beneath mountains, detectors like LUX Zeppelin and Xeno NNT wait in profound silence, shielded from cosmic rays, hoping to record the minuscule vibration or flash of light that would signal a WIMP bumping into an atomic nucleus. Meanwhile, particle smashers like the Large Hadron Collider are trying to create dark matter particles by recreating the high-energy conditions of the early universe. Perhaps the most visually striking proof of dark matter's existence comes from observations of colliding galaxy clusters, like the famous Bullet Cluster. When two clusters smash into each other, the clouds of hot, visible gas that make up most of their normal matter collide and slow down, creating a drag. But astronomers can map the cluster's total mass by observing how their gravity bends light from background galaxies, an effect called gravitational lensing. In the Bullet cluster, the map reveals that the bulk of the mass, the dark matter, has sailed right through the collision, completely separate from the slowed-down gas. This is a direct demonstration that most of the matter is not only dark but also fundamentally different. It doesn't interact with itself or normal matter in any significant way, apart from gravity. This leads to a truly mind-bending reflection. If dark matter makes up over a quarter of the universe and is literally everywhere, passing through our planet, our homes, and our bodies at every moment, how does its complete invisibility challenge our most basic senses? We are evolutionarily tuned to perceive the world through light and matter interactions, yet the dominant form of matter in the cosmos is completely hidden from that perception. What kind of revolutionary technologies will it take to finally pull back the veil? The answer might lie in even more sensitive next-generation detectors, or in space telescopes mapping the subtle distortions of dark matter filaments across the sky, or perhaps in a theoretical breakthrough we can't yet imagine. The immense complexity of this single riddle, the enigma of dark matter, highlights that no single nation or lab can solve it alone. It is a global, collaborative effort uniting physicists, astronomers, and engineers in one of the greatest scientific adventures of all time. Now, let's stretch our minds around an even more baffling concept. Imagine the universe as a balloon, but not one that's being steadily inflated by someone's breath. Instead, picture it as a balloon that somehow started to blow itself up, and it's doing so at a faster and faster rate, with no end in sight. The force driving this ever-accelerating expansion is what scientists call dark energy, and it's not just a small player. It makes up a staggering 68% of the entire cosmos. This discovery in the late 1990s was so revolutionary that it completely overturned the long-held assumption that the universe's expansion, set in motion by the Big Bang, should be gradually slowing down due to the relentless pull of gravity. Two independent teams of astronomers were racing to measure the distances to far-off supernova, and they both arrived at the same shocking conclusion. The universe isn't just expanding, it's speeding up. This monumental finding earned the leaders of those teams the Nobel Prize in Physics in 2011, and fundamentally rewrote our cosmic story. Cosmologist Adam Rees, who was one of those Nobel laureates, captured the sheer magnitude of this mystery when he stated that dark energy is the most profound puzzle in physics today, as it dictates the ultimate fate of everything. It is the dominant component of the universe, the master conductor of cosmic destiny, and yet we have almost no idea what it actually is. So, what are the leading theories trying to explain its nature? One compelling idea is that dark energy is an intrinsic property of space itself. Empty space, according to quantum physics, is not truly empty. It seethes with virtual particles popping in and out of existence. This vacuum energy could generate a repulsive force, a concept that Albert Einstein himself actually proposed and then later discarded as his greatest blunder. He called it the cosmological constant. If this is the correct explanation, then dark energy's strength would remain constant over time, leading to a universe that expands forever at an ever-increasing rate, eventually becoming a cold, dark, and incredibly lonely void as galaxies are pushed apart beyond the visible horizon. Another fascinating possibility is that dark energy is not constant at all, but a dynamic force field that has changed over the life of the universe. Theorists call this concept quintessence, named after the fifth element of ancient philosophy. Unlike the static cosmological constant, quintessence could evolve, its strength either increasing or decreasing over billions of years. This opens up even more dramatic possibilities for the cosmos's final act. If this field were to grow in strength, it could lead to a terrifying scenario known as the Big Rip. In this fate, the repulsive force of dark energy would eventually overcome all other forces in nature. It would first tear apart galaxy clusters, then individual galaxies, then stars from their planetary systems. In the final moments, it would rip apart planets' molecules and even atoms themselves, shredding the very fabric of spacetime. The fate of the entire cosmos hinges on which of these ideas, if either, is correct. The key to understanding how dark energy drives this acceleration lies in a concept with a counterintuitive name: negative pressure. In our everyday experience, pressure pushes things outward like in an inflated tire. But in the strange realm of cosmology, a sufficiently negative pressure within the fabric of space can act as a sort of anti-gravity, causing the expansion of the universe to speed up instead of slow down. This idea is woven right into the fabric of Einstein's equations of general relativity, which describe how matter and energy shape the geometry of spacetime. The discovery of dark energy was the moment we realized that the dominant form of energy in the universe behaves in this profoundly strange way. To map the effects of this mysterious force, astronomers are using the most powerful tools at our disposal, like the James Webb Space Telescope. By peering back in time at the most distant galaxies and supernova, these observatories are helping us measure precisely how the rate of expansion has changed over billions of years, allowing us to test whether dark energy is truly constant or dynamic. We can even find the fingerprints of dark energy's influence stamped onto the very first light in the universe, the cosmic microwave background. This faint afterglow of the Big Bang is a snapshot of the cosmos when it was just 380,000 years old. By studying the tiny fluctuations in this background radiation, satellites like the Planck mission have been able to measure the total content of the universe with incredible precision. The patterns in this ancient light confirm that dark energy, even in the universe's infancy, was already beginning to shape its large-scale structure and destiny. So here is a question to sit with for a moment. How is it that an energy we cannot see, touch, or directly measure holds such absolute control over the long-term fate of everything, every galaxy, every star, every planet, and every one of us? What does the existence of such a dominant yet invisible component of reality tell us about the limits of our own perception and knowledge? This profound mystery, the enigma of dark energy, forces us to confront the possibility that the most powerful forces in the cosmos are not the ones we can easily observe, but are hidden in the silent, empty spaces between the stars. This realization naturally draws our curiosity toward other hidden aspects of reality, like the very structure of space and time, and the possibility that our universe is just one layer of a much deeper, multidimensional reality. Now rewind the cosmic clock back to the very beginning, to a time so brief it's almost impossible to fathom the first fraction of a second after the Big Bang. In that unimaginably fleeting moment, something truly spectacular happened. The universe didn't just expand, it exploded in size at a rate that defies all intuition, undergoing a phenomenal growth spurt known as cosmic inflation. In less time than it takes to blink, a region of space smaller than a single subatomic particle was stretched to a size larger than our entire observable universe today. This wasn't a gentle unfolding, it was a violent, exponential stretching of the very fabric of reality, a process that took a potentially lumpy, chaotic newborn cosmos and ironed it out into the remarkably smooth and uniform universe we observe on the largest scales. Yet, for all the order it created, this event left behind a trail of tantalizing clues. the most famous being the incredible uniformity of the cosmic microwave background radiation, that ancient light from the dawn of time. The theory of inflation was first proposed in the 1980s by physicist Alan Guth, who was trying to solve several deep problems with the standard Big Bang model. He realized that a period of ultra-fast expansion could elegantly explain why the universe appears so similar in all directions, a feature known as isotropy. Without inflation, regions of the universe on opposite sides of the sky would never have had time to communicate and reach the same temperature. They were simply too far apart. But if the entire observable universe was once a tiny, connected speck that was then inflated to colossal size, it makes perfect sense that it would have the same properties everywhere. While inflation beautifully solves this horizon problem, it immediately raises two even more profound questions. What in the world could have triggered such a fantastically violent event? And what mysterious force caused it to suddenly turn off, allowing the slower, more sedate expansion we live with today to take over? To understand the mechanics, we need to introduce the concept of a scalar field, often called the Inflaton field. Think of this as a kind of energy field that permeated all of space in the earliest moments. This field was trapped in a state of high energy, like a ball perched at the very top of a steep hill. This high-energy state possessed a peculiar property. It generated a powerful repulsive gravity, forcing space to stretch at an exponential rate. As the universe expanded, the Inflaton field slowly rolled down its energy hill. When it finally reached the bottom, this enormous pent-up energy was released in a tremendous burst, flooding the universe with hot particles and radiation, effectively kick-starting the traditional hot Big Bang we read about in textbooks. The tiny quantum fluctuations that were present in that field during its rapid roll were also stretched to enormous sizes, and it is these minute ripples that eventually, over billions of years, served as the gravitational seeds for all the cosmic structure we see today. The vast web of galaxies, clusters, and superclusters. The quest to prove inflation is a dynamic and ongoing scientific adventure. One of the most promising lines of evidence comes from looking for a specific pattern, called B-mode polarization, imprinted on the cosmic microwave background. This faint swirling pattern in the ancient light would be the direct signature of primordial gravitational waves, ripples in spacetime itself generated by the violent tremors of the inflationary expansion. The search for this signal has been full of drama. In 2014, the BICEP 2 experiment, a powerful telescope at the South Pole, made headlines around the world with an initial announcement that they had detected this telltale pattern. The scientific community erupted with excitement, but further analysis revealed that the signal was largely contaminated by interstellar dust within our own galaxy. This episode, while a setback, perfectly illustrates the cutting-edge nature of this field, where the stakes are incredibly high and the path to discovery is never straightforward. This leads to one of the most mind-expanding implications of inflation, championed by physicists like Andre Linde. His theory of eternal inflation suggests that once started, the process may never truly stop. In this picture, the overall inflating space, called the multiverse, continues to expand forever. But within it, random quantum fluctuations can cause tiny pockets to stop inflating, each one bubbling off to become its own separate, self-contained universe, perhaps with completely different physical laws and constants. Our entire cosmos, in this view, would be just one bubble in a vast, frothing cosmic sea of universes. So we are left with a deeply philosophical question that bridges science and identity. If this inflationary picture is correct, and our universe is just one of a potentially infinite number, how does that reshape our sense of self? Are we unique or simply residents of one bubble among countless others? our physical laws just one random draw in a cosmic lottery. This staggering idea of a multiverse, a reality composed of multiple realities, naturally pulls our gaze toward the possibility that other dimensions, hidden from our everyday perception, could be the very framework that makes such a vast and varied cosmic landscape possible. Imagine the year is 1912, and an intrepid Austrian physicist named Victor Hess is embarking on a daring series of balloon flights, ascending high into the atmosphere, into regions so thin that the air is difficult to breathe. His mission is to investigate a puzzling phenomenon. Electroscopes, instruments that measure electric charge, were mysteriously discharging at ground level. The prevailing theory was that radiation from the Earth itself was the cause, but Hess suspected something else. As his balloon climbed higher, past 5,000, then 10,000 feet, he made a startling discovery. Instead of decreasing, the radiation levels actually increased dramatically. He had made the first definitive proof that an invisible rain of high-energy particles was constantly bombarding our planet from the depths of space. He called this phenomenon Herrnstrahlung, or radiation from above, and in that moment the field of cosmic ray astronomy was born, earning him a Nobel Prize and opening a window into the most violent corners of the universe. These cosmic rays are not rays of light, but rather a relentless shower of subatomic particles, mostly protons and the nuclei of atoms like helium, iron, and even heavier elements, all stripped of their electrons and accelerated to velocities approaching the speed of light. They are the fastest, most energetic particles known to exist in nature, and they carry with them the unmistakable signature of the colossal events that created them. As Nobel laureate Arthur Compton so poetically described them, cosmic rays are messengers from the depths of space, carrying stories of violent events we are only beginning to decode. They are the forensic evidence of stellar explosions, the exhaust fumes from feasting black holes, and perhaps even the telltale signs of physics we have yet to imagine. Yet, for over a century, their precise origins have remained one of astronomy's most enduring riddles, a cosmic whodunit on a galactic scale. The central enigma of cosmic rays lies in their energy and their journey. While we know that many of the lower energy cosmic rays come from within our own Milky Way galaxy, likely accelerated by the expanding shock waves of supernova explosions, the ultra-high energy cosmic rays present a profound puzzle. These are particles with energies so immense they are difficult to comprehend, carrying the kinetic energy of a professionally thrown baseball, but compressed into a single subatomic particle. According to our current understanding of physics, such particles should not be able to travel vast cosmic distances. As they race through the universe, they should interact with the faint sea of photons that make up the cosmic microwave background radiation, the leftover heat from the Big Bang. These interactions would sap their energy over millions of light years, effectively putting a speed limit on how far they can travel. The fact that we detect them here on Earth means they cannot have come from the distant, early universe. They must be relatively local, cosmic neighbors generated by some nearby, unimaginably powerful particle accelerator. This points the investigation toward the most extreme and energetic objects in our cosmic backyard. The prime suspects are active galactic nuclei, the supermassive black holes at the centers of galaxies that are actively consuming vast amounts of gas and dust. As matter spirals into these gravitational monsters at nearly the speed of light, it can be funneled into powerful jets that blast out across space for thousands of light years. These jets are perfect candidates for natural particle accelerators, capable of energizing protons and atomic nuclei to the incredible levels we observe. Other potential sources include gamma-ray bursts, the spectacular deaths of massive stars, or perhaps even the violent collisions of entire galaxies. Yet, when we point our telescopes at the directions from which the highest energy rays arrive, we often find no obvious cataclysmic source, leaving us to wonder if our catalogue of cosmic violence is still incomplete. To catch these elusive messengers, scientists have built some of the most ambitious observatories on Earth. The Pierre Auger Observatory in Argentina, for instance, spans an area of over 3,000 square kilometers, an array of 1,600 water tanks spaced across the Pampas Plains. When an ultra-high-energy cosmic ray slams into the Earth's atmosphere, it creates a massive cascade of secondary particles, an extensive air shower that spreads out for kilometers. These particles hit the water in the tanks, producing faint flashes of blue light called Cherenkov radiation, which sensitive photomultiplier tubes then record. By analyzing the timing and intensity of these signals across the vast array, researchers can trace the path of the original cosmic ray back through the atmosphere and estimate its energy and incoming direction with remarkable precision. The plot thickens when we examine the cosmic ray energy spectrum, a graph that shows how many particles arrive at different energy levels. This spectrum holds a peculiar feature known as the ankle, a point where the number of particles at a certain energy dips and then changes slope. This ankle is thought to be a critical clue, marking the transition between two different populations of cosmic rays. Below the ankle, we are likely seeing particles accelerated within our own galaxy. Above the ankle, we enter the realm of the ultra-high-energy cosmic rays, which are believed to be extragalactic in origin. This suggests that the processes that create the most energetic particles in the universe are fundamentally different from the supernova that produce the galactic ones, pointing to those even more powerful and mysterious extragalactic engines. The sheer power of these cosmic accelerators was brought into stunning focus in October 1991, when the Fly's Eye Cosmic Ray Detector in Utah recorded an event that left physicists in a state of disbelief. A single atomic nucleus, likely a proton, struck the atmosphere with an energy of about 300 exa-electron volts. This value was so phenomenally high that it was immediately dubbed the "Oh my God" particle. To put this in perspective, this one subatomic particle carried kinetic energy millions of times greater than what the most powerful human-made particle accelerator, the Large Hadron Collider, can produce. It was a stark and humbling reminder that nature has been running a far more energetic laboratory for billions of years, and we are only just beginning to understand its capabilities. This leads to a final, tantalizing possibility. Could some of these mysterious cosmic rays, particularly those with specific energy signatures, be the indirect signal of something even more exotic, like dark matter? One theoretical possibility is that dark matter particles, accumulated in the dense cores of celestial bodies like the Sun or the galactic center, could occasionally collide and annihilate each other, producing a shower of standard model particles, including protons and nuclei that would look just like cosmic rays. While no definitive signal has been found, this potential link adds another layer of urgency to the search, turning cosmic ray observatories into indirect dark matter detectors. So we are left with a truly fundamental question, one that pushes at the boundaries of known physics. What kind of cosmic engines, what unfathomable forces of nature can possibly produce particles with energies that dwarf anything we can create on Earth? And if the sources are indeed nearby, active galactic nuclei or colliding galaxies, why do their signals often seem to point toward empty space? The answers to these questions will not only reveal the identity of these celestial accelerators, but could very well force us to rewrite the rules of particle physics and high-energy astrophysics, hinting that the solutions may lie in realms beyond our current dimensional understanding. Think of the universe as a vast, seemingly endless ocean. We know the ingredients for life are abundant, like the water and nutrients that fill our seas. We have discovered thousands of planets orbiting distant stars, with billions more likely existing in the habitable zones where conditions could be just right. The numbers are staggering. The potential for life to arise elsewhere seems almost a mathematical certainty. And yet, when we lower our microphones into this cosmic sea, when we train our most powerful telescopes on the depths of space, we are met with a profound and unsettling silence. This is the heart of the Fermi Paradox, a puzzle famously crystallized by physicist Enrico Fermi during a casual lunch conversation in 1950. Looking at the sheer scale and age of the galaxy, with its billions of suns and potential for civilizations millions of years older than our own, he asked the deceptively simple question that has echoed through the decades: where is everybody? The silence is not for a lack of trying. For over 60 years, projects under the umbrella of SETI, the search for extraterrestrial intelligence, have been meticulously scanning the heavens, listening for any artificial signal, any pattern in the radio noise that would shout, "We are here." These efforts, led by dedicated astronomers, have covered millions of frequencies and examined countless star systems, but the result so far is a resounding quiet. As Jill Tarter, a true pioneer of this search, has reflected, the universe is both vast and ancient, and this silence forces us to confront two deeply unsettling possibilities. It could mean that there is a great filter ahead of us, a barrier so formidable that almost no civilization survives it, making us not latecomers but tragically early. Or it could be a stark testament to our own profound uniqueness, a lonely fluke in an otherwise sterile expanse. To make sense of this cosmic quiet, scientists have developed a wide spectrum of theories, each attempting to solve the paradox. One of the most compelling and sobering is the Great Filter hypothesis. This idea suggests that the evolution of life from simple origins to a spacefaring, technologically advanced civilization requires navigating a series of critical steps. Perhaps the filter lies in the very origin of life, an event so statistically improbable that it has only happened once. Maybe it is the jump from simple single-celled organisms to complex multicellular life, which took billions of years on Earth. Or, and this is the most concerning possibility, the great filter lies in our future. It could be that almost all intelligent species inevitably discover technologies that lead to their own destruction, whether through nuclear war, environmental collapse, or a runaway artificial intelligence. In this grim scenario, the silence is a graveyard, and we have yet to hear the funeral bells. Other theories offer different, equally fascinating explanations. Perhaps advanced civilizations are out there, but they have moved so far beyond our primitive radio technology that their methods of communication are completely undetectable to us. We might be like an isolated tribe listening for smoke signals, while the rest of the galaxy is communicating with a form of physics we haven't yet discovered, using neutrino streams or quantum entanglement. Another popular idea is the zoo hypothesis, which posits that advanced extraterrestrials are fully aware of our existence, but have chosen to place us in a kind of cosmic quarantine or a galactic nature preserve. They are observing us from a distance, allowing humanity to develop naturally without interference, only making contact once we have reached a certain level of maturity or peace. This would resolve the paradox by suggesting the cosmos isn't empty. It's just that everyone is politely and silently watching. To quantify our chances of ever making contact, astronomers often turn to the Drake equation. This isn't a single solution, but rather a framework for thinking about all the variables involved. It multiplies factors like the rate of star formation, the fraction of stars with planets, the number of habitable planets per system, the fraction where life actually appears, the fraction where life becomes intelligent, the fraction that develops detectable technology, and finally, the length of time such civilizations release signals into space. Plug in optimistic numbers and the galaxy should be buzzing with conversation. Use more conservative estimates, and the number of active, communicative civilizations could be very small, perhaps even just one, us. The equation highlights that even if life is common, the specific chain of events that led to a technological civilization on Earth, with its stable sun, protective Jupiter, and large moon, might be exceptionally rare. We even see this tension play out in real astronomical observations. Take the strange case of KIC 8462852, better known as Tabby's star. Astronomers noticed its light would dim by enormous and irregular amounts, sometimes up to 22%. This was far too much to be caused by a passing planet. The bizarre light curve sparked a flurry of speculation, including the tantalizing, though highly speculative, idea that we were witnessing a vast alien megastructure, like a swarm of energy-collecting satellites orbiting the star. While follow-up studies have pointed to more natural explanations like clouds of dusty debris, the episode perfectly captures our dilemma. When faced with a phenomenon we cannot immediately explain, our minds leap to the most extraordinary possibility, highlighting our deep-seated desire to find company in the cosmos. So we are left circling back to that fundamental, almost spiritual question. In this immense and ancient universe, are we truly, utterly alone? Or is the cosmos teeming with civilizations that are, for reasons beyond our current understanding, hiding in plain sight, their presence camouflaged by technology, distance, or dimensional barriers we cannot yet perceive? This profound paradox does more than just challenge our scientific models. It forces us to look inward and contemplate our own future. The search for an answer is not just about finding others. It is about understanding what it means to be a conscious, technological species in a universe that offers no easy answers. Back in the 1970s, astronomers mapping the grand, swirling motions of galaxies across the heavens stumbled upon something profoundly unsettling. It wasn't just that galaxies were moving apart due to the universe's expansion. It was that our own Milky Way, along with our entire local group of galaxies and thousands of others, appeared to be caught in a vast, silent river, all streaming relentlessly toward a specific point in the sky, toward an unseen something of unimaginable mass. This mysterious gravitational anchor was dubbed the Great Attractor, and its location posed a significant problem. It lies in the direction of the constellation Centaurus, directly behind the crowded, dusty central plane of our own Milky Way galaxy, a region so obscured by gas, dust, and stars that astronomers call it the zone of avoidance. It is quite literally a colossal blind spot in our cosmic vision, a place where our view of the distant universe is almost completely blocked, hiding a gravitational giant that commands the motion of our entire galactic neighborhood. The sheer scale of this force is difficult to overstate. The Great Attractor exerts a gravitational pull equivalent to millions of billions of suns, a mass so immense that it warps the very flow of galaxies across hundreds of millions of light years. This discovery fundamentally challenged our maps of cosmic motion. It revealed that the universe isn't just expanding smoothly, it's also filled with these subtle, powerful currents and tides, driven by the uneven distribution of matter on the grandest scales. As the astrophysicist Alan Dressler so evocatively put it, the Great Attractor is a reminder that our view of the cosmos is obscured, and there are giants lurking in the shadows. We were like sailors on a vast ocean, feeling a powerful current tugging our ship, but unable to see the massive, hidden continent that was its source. To pierce through this cosmic veil, scientists had to turn to eyes that could see beyond ordinary light. Using powerful infrared and radio telescopes, which can peer through the dense dust clouds that block visible light, astronomers began to map what lay in the zone of avoidance. What they found was not one single supermassive object, but an incredibly dense and rich confluence of galaxies, a massive galaxy cluster known as the Norma cluster. This cluster, located about 220 million light-years away, acts as the bright, visible heart of the Great Attractor region. Yet, when astronomers added up all the mass from the thousands of galaxies and the hot gas they could detect in this region, it still wasn't nearly enough to account for the tremendous gravitational pull they were measuring. The majority of the mass, it seemed, was not in the visible galaxies at all, but in the form of an enormous, concentrated halo of dark matter, the invisible scaffolding that holds these cosmic structures together and provides the extra gravitational muscle. This discovery placed the Great Attractor at the center of a much larger story, one that redefined our cosmic address. In 2014, a team of astronomers unveiled a new map of our local universe, revealing that our Milky Way is just a tiny part of a colossal supercluster of galaxies they named Laniakea, a Hawaiian word meaning immense heavens. The Great Attractor serves as the central gravitational anchor for this vast cosmic metropolis. Laniakea is not a tightly bound cluster, but a sprawling web of galaxy groups and clusters, all flowing along invisible filaments of dark matter toward the same gravitational basin, the Great Attractor. Think of it not as a destination, but as the bottom of a valley in the landscape of the cosmos. Every galaxy in our supercluster is sliding down the slopes of this gravitational watershed toward its center. Our sun, our planet, and everything we know is caught in this slow, majestic drift. Mapping this flow required a clever application of a fundamental astronomical tool, redshift surveys. By carefully measuring the redshift of thousands of galaxies, the stretching of their light as they move away from us due to the universe's expansion, astronomers can detect tiny deviations from the smooth Hubble flow. These deviations reveal the galaxy's peculiar velocities, their individual motions superimposed on the general expansion. It was precisely these meticulous measurements that revealed the coherent stream of galaxies toward the Great Attractor. But the plot thickens when you look even further. Our entire Laniakea supercluster, with the Great Attractor at its heart, is itself being pulled. The gravitational influence of an even larger and more massive structure, the Shapley supercluster, located over 600 million light-years away, is tugging on us. So we have a cosmic tug of war on an epic scale. The Great Attractor pulls us in, while the Shapley supercluster pulls us further still, creating a complex map of gravitational influences that stretches across nearly 1 billion light-years. This grand puzzle forces us to confront a truly fundamental question about the architecture of the cosmos. What invisible frameworks, what hidden concentrations of dark matter and galaxies are truly governing the motion of everything we see? The Great Attractor and the Shapley supercluster are not isolated anomalies. They are likely just two of the most prominent knots in a vast, universe-spanning cosmic web, a structure built from dark matter and illuminated by the galaxies that cluster along its filaments. Our ability to perceive this web is limited by what we can see, but through the motions of galaxies we can feel its pull. This investigation into the large-scale flow of the cosmos, driven by unseen masses, naturally compels us to wonder if our current understanding of gravity itself is complete, or if the strange behavior we observe on these immense scales could be a hint of something even more profound, like the influence of hidden dimensions warping the fabric of space in ways we are only beginning to imagine. Let's perform a thought experiment. Rewind the cosmos back to its very first moments, a seething, dense fireball of pure energy. As the universe expanded and cooled, that energy should have condensed into pairs of particles and their mirror opposites antiparticles. For every electron, a positron should have been born. For every quark, an antiquark. Matter and antimatter are perfect counterparts in every way except for their opposite charges. And when they meet, they annihilate in a flash of pure energy, leaving nothing behind. According to this perfect symmetry, the early universe should have been a vast, efficient furnace of mutual destruction. Every particle of matter should have found its antimatter twin, and they should have vanished together, leaving behind a cosmos filled with nothing but fading light. There should be no atoms, no planets, no stars, and certainly no one to ponder this very question. And yet, here we are. The fact that you, I, and the entire visible universe exist is proof that this perfect symmetry was broken. Somewhere in that first fleeting second, a tiny, almost imperceptible preference for matter over antimatter emerged. This is the Barrian asymmetry problem, and it is not just an academic curiosity. It is the fundamental reason anything at all exists today. Experiments and observations have pinned down the scale of this miracle. For every billion annihilations that occurred in the early universe, roughly one single particle of matter was left over. 1 in a billion, that minuscule surplus is all that accounts for every galaxy, every star, and every living creature in the cosmos. It is the ultimate case of winning a cosmic lottery with astronomically long odds. But what mechanism could possibly have tilted the scales so precisely? The brilliant Soviet physicist and dissident Andrei Sakharov laid out the 3 essential conditions needed for such an asymmetry to arise. First, the universe must have been out of thermal equilibrium, meaning it wasn't in a uniform, stable state, a condition easily satisfied by its rapid, violent expansion. Second, there must be processes that violate the conservation of Barrian number, essentially allowing the total amount of matter to change. And third, there must be a violation of both charge conjugation C and parity P symmetry. This means the laws of physics must treat particles and antiparticles differently, and they must also distinguish between right-handed and left-handed configurations. We have actually observed one piece of this puzzle in action, CP violation. In certain rare subatomic processes, particles and their antiparticles do decay at slightly different rates. This was first discovered in the decay of neutral kaons in the 1960s and later confirmed in studies of B mesons. However, the amount of CP violation we have measured within the standard model of particle physics is far, far too small to account for the overwhelming matter dominance we see in the universe. It's like finding a single drop of water when you need to fill an entire ocean. As researchers at CERN often emphasize, solving the Barrian asymmetry problem is almost guaranteed to reveal entirely new particles or forces beyond our current understanding. It is a direct pathway to physics that lies outside the standard model. This has led theorists to propose some truly elegant and profound mechanisms. One leading candidate is leptogenesis. This theory suggests that the initial imbalance might have begun not with quarks, but with the ghostly, nearly massless particles known as neutrinos. In the early universe, incredibly heavy, hypothetical right-handed neutrinos could have decayed. If these decays violated CP symmetry, they would have produced a slight excess of ordinary matter leptons, like electrons and neutrinos, over their antimatter counterparts. Through a complex cascade of interactions known as Sphaleron processes, this lepton asymmetry could then have been converted into the Barrian asymmetry we see today in protons and neutrons. It's a compelling idea that connects the mystery of our existence to the equally mysterious properties of neutrinos. Another fascinating avenue is electroweak baryogenesis. This theory places the crucial moment of symmetry breaking later in cosmic history during the electroweak phase transition. As the universe cooled, the Higgs field, which gives particles their mass, settled into its current state. If this transition was a sharp, sudden phase change like water freezing into ice, it could have created the out-of-equilibrium conditions Sakharov required. Bubbles of the new phase would have expanded through the cosmos, and within their walls, interactions with the Higgs field could have preferentially generated more matter than antimatter. The challenge is that for this to work, the Higgs boson likely needs to have properties that we haven't yet observed, making it a prime target for investigation at the Large Hadron Collider. The role of cosmic inflation in this story is also critical. Even if a small asymmetry was generated by one of these mechanisms, the tremendous, exponential expansion of space during inflation would have diluted any pre-existing matter and antimatter to virtually nothing. This implies that the process that created our 1 in a billion surplus must have occurred after inflation, repopulating the universe with a biased slate of particles. This timing is a crucial constraint for any viable theory. The search for answers also drives experiments that look for the ultimate instability of matter. If baryon number is not perfectly conserved, then the proton, the building block of all atoms, should not live forever. Grand unified theories, which attempt to merge the electromagnetic, weak and strong forces, often predict proton decay. Massive detectors like Super Kamiok and in Japan, filled with ultra-pure water deep underground, have watched for decades for the telltale flash of light from a single proton decaying. So far, none have been seen, telling us that if protons do decay, their lifetime is staggeringly longer than 10 to the 34 years. This null result itself helps rule out certain models and guides us toward others. So we are left to contemplate the sheer improbability of it all. How did a fragility in the laws of physics, a tiny crack in the perfect mirror of symmetry, lead to a universe filled with complex structure and life? That 1 part in a billion preference for matter was the seed for everything we hold as real. It determined the ultimate fate of the cosmos, ensuring it would be made of something rather than nothing. This fundamental question about initial conditions pushes us to consider whether the answer lies in realms we cannot directly perceive. Could the presence of hidden dimensions have subtly influenced the fields responsible for this asymmetry, providing the extra leverage needed to tip the scales? The quest to understand why we exist at all is perhaps the deepest motivation for exploring the most hidden layers of reality. Now, let's confront a paradox that strikes at the very heart of causality. When we look at the cosmic microwave background, the oldest light in the universe, we see something deeply puzzling. In one direction, the temperature of this afterglow is 2.725 degrees above absolute zero. If we point our telescopes in the exact opposite direction of the sky, billions of light years away, we measure precisely the same temperature. This incredible uniformity is a problem, a profound one known as the horizon problem. The issue is that these two vastly separated regions of the universe have not had enough time since the Big Bang to exchange heat or information and reach this identical temperature. According to the standard Big Bang model, they were forever beyond each other's cosmic horizon, never in causal contact. It's as if you walked into a vast, crowded room and found that every single person, even those on opposite sides who have never met or communicated, were all wearing the exact same outfit down to the smallest detail. This shouldn't happen by chance. It demands an explanation. The most widely accepted solution to this riddle is the theory of cosmic inflation. This idea proposes that in the very first fraction of a second of the universe's existence, it underwent a breathtakingly brief period of exponential expansion, inflating from a subatomic speck to a size larger than the entire observable cosmos. Before this inflation occurred, the entire universe we see today was a tiny, interconnected region. Every part of it was in intimate contact with every other part, allowing heat and energy to mix thoroughly, creating a perfectly uniform temperature. Then, inflation acted like a cosmic zoom lens, stretching this tiny, smooth patch to an immense scale, preserving its uniformity while pushing formerly adjacent regions to opposite ends of the visible sky. This elegant idea resolves the horizon problem by ensuring that the entire observable universe was once causally connected, long before the rapid expansion drove its parts apart. However, as cosmologist Paul Steinhardt, a co-developer of an alternative called the cyclic model, compellingly argues, inflation might not be the only way to achieve uniformity, urging us to think beyond standard paradigms. While inflation is a powerful and popular idea, it is not the only game in town. Other theorists have proposed fascinating alternatives that also seek to explain the smoothness of the cosmos. One such concept is the variable speed of light hypothesis, which suggests that in the extremely early universe, the speed of light was vastly greater than it is today. If light could travel infinitely faster in that primordial epoch, then distant regions could have communicated and equalized their temperatures, solving the horizon problem without the need for inflation. Another radical set of ideas falls under the banner of cyclic or bouncing universes. In these models, our Big Bang was not the absolute beginning but rather a transitional phase, a big bounce from a previous contracting universe. In this scenario, the universe we see was smoothed out over an immensely long period of contraction in a prior cosmic cycle, and the bounce into our current expanding phase simply preserved that pre-existing uniformity. To truly appreciate the problem, we need to break down the core issue of causality. According to Einstein's special relativity, no information or influence can travel faster than the speed of light. In the roughly 13.8 billion years since the Big Bang, light has only had time to travel a finite distance, about 13.8 billion light-years. This defines our observable horizon, yet the uniformity of the cosmic microwave background extends across regions that are now separated by over 90 billion light-years. Without a mechanism like inflation, which effectively allows for superluminal expansion of space itself, note that this doesn't violate relativity, as it is space expanding, not objects moving through space. These regions would have required some form of faster-than-light communication to synchronize their properties. Inflation elegantly sidesteps this violation by moving the period of causal contact to a time before the inflationary growth spurt, when the entire universe was a tiny, cozy, and connected neighborhood. Our most precise understanding of this early uniformity comes from incredibly detailed maps of the cosmic microwave background, most famously from the Planck satellite. This mission measured the temperature of the CMB with microkelvin in precision across the entire sky. While the background is stunningly uniform, the Planck data also revealed the all-important tiny anisotropies, minuscule fluctuations in temperature, variations of just 1 part in 100,000. These tiny ripples are the fossilized imprints of quantum fluctuations that were stretched to cosmic proportions during inflation. They are the seeds of all future structure. The slightly denser regions in this map are the gravitational wells that would eventually pull in matter to form the vast cosmic web of galaxies and clusters we see today. So the CMB does two things at once. Its overwhelming smoothness points to a period of intense smoothing like inflation, while its tiny, specific patterns of imperfection tell us exactly what kind of quantum seeds were planted during that epoch. Inflation also handily solves another related puzzle known as the monopole problem. Grand unified theories which attempt to merge the electromagnetic, strong, and weak nuclear forces predict that the early universe should have been flooded with bizarre, heavy relics called magnetic monopoles. These particles, which are like isolated north or south magnetic poles, should be incredibly massive and stable, meaning they should still be around today. Yet, despite extensive searches, not a single magnetic monopole has ever been conclusively detected. Inflation explains their absence beautifully. If these monopoles were created before or during the inflationary period, the fantastic stretching of space would have diluted their density to virtually zero, spreading them so thinly across the cosmos that the chance of one passing through our entire solar system is infinitesimally small. Their observed absence becomes a powerful, if indirect, piece of evidence supporting a period of rapid inflation. So we are left with a compelling, yet still open, investigation. The inflationary paradigm is a powerful and elegant framework, but it is not yet a proven fact. The quest to find definitive proof, such as the specific pattern of primordial gravitational waves imprinted on the CMB, continues. This leads us to a profound and speculative question. If inflation is not the final answer, what other force or principle could have made the infant universe so incredibly homogeneous? Does the profound smoothness of our cosmos hint at a deeper layer of reality, perhaps one where the fundamental constants were set differently, or where the fabric of spacetime is woven with extra, hidden dimensions that naturally enforce a kind of cosmic uniformity from their higher dimensional perspective? The search for the answer to the horizon problem is more than a technical debate. It is a journey to understand the very first moments of cause and effect, and how our magnificent, structured universe emerged from a state of perfect primordial calm. In the world of physics, few predictions are as elegant and as stubbornly unfulfilled as that of the magnetic monopole. The story begins in the 1930s with the brilliant and deeply insightful physicist Paul Dirac. While working on the mathematics that described the electron and its interaction with electromagnetic fields, he made a startling theoretical discovery. His equations suggested that for the universe's account books to balance, for electric charge to be quantized in neat, discrete units, there should exist a fundamental particle carrying a solitary magnetic charge, an isolated north pole without a south, or a south pole without a north. This was a revolutionary idea. Every magnet we have ever found, from a simple refrigerator magnet to the Earth itself, is a dipole with two inseparable poles. Break a bar magnet in half, and you don't get a separate north and a separate south. You get two new, smaller dipoles. Dirac's monopole promised to shatter this symmetry, offering a new, fundamental building block of reality that was as basic as the electron itself. The implications of this discovery only grew with time. As physicists developed grand unified theories, ambitious frameworks aiming to merge the electromagnetic, weak, and strong nuclear forces into a single, elegant description, the magnetic monopole became more than just a possibility. It became an inevitability. These theories suggest that in the unimaginably hot, dense first moments after the Big Bang, all the forces of nature were unified into one superforce. As the universe expanded and cooled, it underwent a series of dramatic phase transitions, akin to steam condensing into water or water freezing into ice. Theorists found that these cosmic phase transitions would have had a fascinating side effect. They would have created topological defects in the fabric of spacetime, knots of energy that could not smooth themselves out. And one of the most stable of these defects would be the magnetic monopole. According to this line of thinking, the early universe should have been flooded with these primordial relics, as common in their time as photons are today. And yet, despite decades of meticulous searching, not a single definitive magnetic monopole has ever been found. This glaring absence stands as a direct challenge to some of our most ambitious theories of cosmic unification. The physicist John Preskill perfectly captured the scientific conundrum when he noted, "The absence of monopoles is either a clue that our theories are wrong or that the universe has hidden them from us." This single statement frames the entire predicament. Either our beautiful grand unified theories are fundamentally flawed, missing some crucial piece of physics that prevents monopoles from forming, or the universe has conspired to make these particles so incredibly rare or difficult to detect that they have thus far evaded all our efforts to find them. So, where could all the monopoles have gone? The most compelling and widely accepted explanation involves the cosmic inflation scenario we discussed earlier. If magnetic monopoles were created in the fiery forge of the early universe, the subsequent period of exponential inflation would have stretched spacetime to such an incredible degree that the density of these particles would have been diluted to almost nothing. Imagine sprinkling a teaspoon of salt into a single glass of water. You would easily taste it. Now, imagine taking that same teaspoon of salt and dispersing it evenly throughout all the oceans of Earth. The salt would still be there, but finding a single grain would be a monumental task. Inflation, in this analogy, created an ocean of space so vast that any primordial monopoles are now separated by distances that could encompass entire galactic superclusters, making the chance of one ever passing near our detectors astronomically small. Another fascinating possibility is that monopoles do exist, but not in the simple, free-floating form we imagine. They could be confined within composite structures, bound permanently to other particles or to their own antiparticles in a way that renders their magnetic charge neutralized from a distance. Or their properties might be such that they interact with normal matter in ways we haven't thought to look for, perhaps slipping through our planet and our detectors like ghosts through a wall. Over the years, scientists have cast a wide net in their search. They have scrutinized the cosmic rays that continuously bombard our atmosphere, hoping to spot the unique, high-energy signature of a monopole. They have built sophisticated experiments in deep underground laboratories, shielded from other radiation, waiting for a monopole to trigger a detector. They have even attempted to create them in the world's most powerful particle accelerators, like the Large Hadron Collider at CERN, hoping to replicate the conditions of the early universe for a fleeting moment. So far, all these searches have yielded nothing but tantalizing null results. The theoretical allure of the monopole extends beyond its mere existence. If found, it could help explain one of the universe's subtle but profound mysteries, the quantization of electric charge. Why does all electric charge in the universe appear to come in integer multiples of the electron's charge? Why is there no such thing as a third of an electron's charge? Dirac showed that the mere existence of a single magnetic monopole anywhere in the universe would force electric charge to be quantized in exactly this way. It's a beautiful and deep connection between two seemingly unrelated phenomena. Furthermore, some theories suggest that monopoles would not be passive objects. They could act as catalysts for proton decay. A stable proton is a cornerstone of our current physics, but some grand unified theories predict that protons should eventually decay, albeit over timescales trillions of times longer than the current age of the universe. A magnetic monopole, according to these models, could dramatically speed up this process, providing a potential pathway to detect both the monopole and the underlying theory in one fell swoop. This ongoing quest is embodied by experiments like MO-EDL, the monopole and exotics detector at the LHC. Unlike the massive cylindrical detectors that surround the collision points, MO-EDL is a more passive hunter. It consists of stacks of plastic nuclear track detectors, sheets of material that act like a photographic emulsion. If a heavily ionizing particle like a magnetic monopole, which would leave a unique telltale damage trail, were to pass through these sheets, it would leave behind a permanent, microscopic record that scientists could later analyze. It's a patient, long-term experiment, a trap set for a creature that may or may not exist, reflecting the persistent hope and methodological creativity of the scientific community. The enduring mystery of the missing monopoles forces us to confront a deeply intriguing possibility. Why has nature, which seems to love symmetry and elegant mathematical solutions, apparently gone out of its way to avoid producing these particles in any detectable quantity? Could it be that our current understanding of the early universe's phase transitions is incomplete? Or, taking a more speculative leap, could these elusive particles be hiding in plain sight, not in our three spatial dimensions, but tucked away within the compact, curled-up folds of higher dimensions that string theory and other models propose? In such a scenario, the influence of a monopole might leak into our reality in subtle ways, but the particle itself resides in a realm we cannot directly access. This missing piece of the cosmic puzzle, therefore, does more than just challenge particle physics. It actively invites us to speculate on how unseen realms and hidden dimensions might serve as the ultimate cosmic attic, harboring entities that are fundamental to the workings of reality, yet forever just beyond our immediate grasp. Imagine for a moment that the universe came with a cosmic control panel, a vast board covered in dials and switches, each one governing a fundamental force or a physical constant. The strength of gravity is set by one dial, the power of the nuclear forces by another, the mass of an electron by a third, and the amount of dark energy by a fourth. Now, here is the astonishing part. If you were to reach out and tweak any one of these dials by just the tiniest fraction, by even one part in a million, the consequences would be catastrophic. With the slightest nudge, stars would fail to ignite, atoms would never bond, and the universe would become a lifeless, sterile void, utterly incapable of supporting any form of complexity, let alone conscious life. This isn't science fiction. This is the fine-tuning problem, one of the most profound and deeply puzzling riddles in all of cosmology. It is the observation that the laws of physics and the fundamental constants of nature appear to be exquisitely, almost miraculously, calibrated to allow for our existence. This incredible precision is evident across a breathtaking range of physical phenomena. Consider the force of gravity. If the gravitational constant were just a little bit stronger, the universe would have collapsed back in on itself in a catastrophic big crunch long before stars and galaxies could ever form. If it were slightly weaker, matter would have flown apart so rapidly that no structures could have ever coalesced from the primordial soup. The same razor's edge balance applies to the nuclear forces. The strong nuclear force, which glues protons and neutrons together inside atomic nuclei, has to be just right. If it were even a few % stronger, two protons could stick together easily, and all the hydrogen in the early universe would have fused into helium and then into heavier elements almost instantly. There would be no long-lived stars like our Sun, and no hydrogen left to form water, a molecule essential for life as we know it. If the strong force were slightly weaker, atomic nuclei would never form at all, and the universe would consist of nothing but a diffuse cloud of hydrogen. Perhaps the most beautiful and specific example of this fine-tuning is the case of carbon-12, the very element that is the fundamental building block of life on Earth. For carbon to be created inside stars, something extraordinary has to happen. Inside the fiery cores, two helium nuclei first fuse to form beryllium-8, but this isotope is highly unstable and decays in a minuscule fraction of a second. For carbon to form, a third helium nucleus must collide with the beryllium-8 before it falls apart. The odds of this happening seemed vanishingly small until the physicist Fred Hoyle made a stunning prediction. He reasoned that for carbon-based life to exist, there must be a previously unknown resonant energy state within the carbon-12 nucleus, a precise energy level that would act like a perfect catcher's mitt, dramatically increasing the probability of this three-way collision. He told nuclear experimentalists exactly where to look, and they found it exactly as he had predicted. This carbon-12 resonance is a direct, quantifiable example of the universe's seemingly purposeful tuning, a specific nuclear arrangement without which planets, life, and we ourselves would simply not be here. The puzzle only deepens when we look at the energy of empty space itself, the cosmological constant we encountered with dark energy. The vacuum of space, according to quantum field theory, should be seething with a tremendous amount of energy. Yet when we calculate this theoretical value based on our best physics, we get a number that is a staggering one, followed by 120 zeros times larger than the value we actually observe from the universe's accelerating expansion. If the vacuum energy were anywhere near that large, the repulsive force would have been so immense that it would have ripped the universe apart before galaxies could even begin to form. The fact that this energy is so incredibly small, yet not quite zero, is perhaps the most extreme case of fine-tuning we have ever discovered. Cosmologist Martin Rees, the astronomer royal, has powerfully articulated the weight of this mystery, stating that fine-tuning might indicate a deeper level of physical law we haven't discovered yet. He suggests that we may be on the verge of a paradigm shift, where these seemingly miraculous coincidences are not accidents but clues pointing toward a more fundamental, unified theory that we have yet to uncover. Faced with this overwhelming evidence, scientists and philosophers have proposed several compelling explanations, each with profound implications. One line of reasoning is the anthropic principle, which in its simplest form states that the universe must be compatible with the conscious life that observes it. In other words, we shouldn't be surprised to find ourselves in a universe capable of supporting us, because in a universe that wasn't, we wouldn't be here to ask the question. While this might sound like a tautology, it becomes a powerful tool when combined with the concept of a multiverse. If our universe is just one of an infinite number of universes, each with its own random set of physical constants and laws, then it is no longer surprising that we find ourselves in one of the incredibly rare ones where the dials happen to be set just right for life. The philosopher John Leslie captured this idea with his analogy of a universe-sized lottery win. We have drawn the one in a trillion ticket that allows for our existence, while countless other universes are barren and lifeless. This multiverse idea finds a potential home in the framework of string theory, which suggests the existence of a vast landscape of possible universes. The mathematics of string theory point to an almost unimaginable number of possible stable configurations for the extra dimensions it proposes, a number estimated to be around 10 to the power of 500. Each of these configurations would correspond to a universe with a different set of physical laws and constants. In this cosmic landscape, our universe is just one tiny plot, one specific combination that allows for stars, planets, and life. The fine-tuning we observe, then, is not a miracle but a consequence of a staggering statistical probability played out across an infinite canvas. There is also the fascinating role of observation selection effects to consider. This is the idea that our very presence as observers inevitably skews the data we can collect. We cannot observe the vast majority of universes that are inhospitable to life. we are irrevocably locked into observing the conditions that made our own observation possible, which naturally highlights the life-friendly parameters we see around us. To truly grasp the fragility of our cosmic situation, consider what would happen if we adjusted just one more dial, the strength of the weak nuclear force. This force is responsible for processes like nuclear fusion in stars and the radioactive decay of certain elements. If the weak force were significantly weaker than it is, a crucial step in the early universe would have been disrupted. Shortly after the Big Bang, the universe was a hot plasma of protons and neutrons. The weak force is responsible for converting protons into neutrons and vice versa, maintaining a delicate balance. If it were weaker, this equilibrium would have been lost, resulting in a universe composed almost entirely of hydrogen. Without a sufficient number of neutrons, the formation of heavier elements in stars would have been stifled. There would be no carbon, no oxygen, no iron, none of the complex chemistry required for planets or life. The cosmos would be a much simpler and far lonelier place. So we are left standing before two equally staggering possibilities, each one reshaping our understanding of reality. Is our universe a unique, almost impossibly special place, its laws and constants finely crafted for a purpose we have yet to comprehend? Or is our existence the result of a colossal cosmic dice roll, and we simply find ourselves in one of the fortunate bubbles in an infinite, frothing multiverse where every possible set of physical laws is realized somewhere? This question of whether our universe is a custom-built home or a lucky draw in a cosmic lottery forces us to confront the very nature of existence, and it is this line of thinking that naturally pulls our gaze toward the architecture that could make a multiverse possible. If countless other universes with different physical laws do exist, where could they possibly be housed? The answer may lie in the very hidden dimensions we have been exploring, with the compactified geometries of string theory providing the separate, isolated domains where these alternate cosmic experiments can play out, each with its own unique tuning of the cosmic control panel. Consider a simple, everyday moment. You watch a drop of ink fall into a glass of clear water. At first, it's a concentrated dark blob, but then it begins to swirl and spread, slowly and irreversibly transforming the entire glass into a uniform, murky liquid. You would be utterly astonished if the process suddenly reversed, if the dispersed ink particles spontaneously gathered back together into a single, neat drop. This intuitive directionality, this one-way street from order to disorder, is a perfect metaphor for the most familiar yet profound puzzle we encounter, the arrow of time. Why does time have a preferred direction, flowing relentlessly from what we call the past toward what we call the future? The truly baffling part is that the fundamental laws of physics, the equations that govern everything from electrons to galaxies, are almost entirely symmetric with respect to time. If you were to take a video of two planets orbiting each other or two electrons colliding and play that video backward, the motion would still obey the laws of physics. The equations of Newton, Einstein, and even Schrödinger work just as well in reverse. So why does our macroscopic experience of reality feel so different? Why do we remember the past but not the future? Why do we see glasses shatter but never spontaneously reassemble? The key to unraveling this mystery lies in a concept from thermodynamics known as entropy, which is essentially a measure of disorder or randomness in a system. The second law of thermodynamics states that the total entropy of an isolated system always increases over time, or at best remains constant. It's the reason the ink diffuses in the water, why your hot coffee cools to room temperature, and why it takes effort to tidy a room, but disorder seems to accumulate all on its own. This ever-increasing entropy gives us a powerful physical definition for time's arrow, the thermodynamic arrow. It points from states of lower entropy, which are more ordered and rare, toward states of higher entropy, which are more disordered and common. But this just pushes the puzzle one step further back. Why was the entropy of the universe so incredibly low in the first place? To understand our present, we have to look all the way back to the beginning. As physicist Sean Carroll so eloquently explains, time's arrow is not built into fundamental laws. It emerges from the specific low entropy state of the early universe. Think of the Big Bang not as a chaotic explosion, but as a moment of incredibly precise and improbable order. The newborn universe was a hot, dense, but remarkably smooth and uniform soup of particles. This was a state of exceptionally low entropy. A completely random, high-entropy state would have been a messy, lumpy, and thermodynamically dull soup with no potential for interesting structure. Instead, we got a cosmos that was, against all odds, beautifully smooth, poised on the edge of a steep entropy hill. From that starting point, the only way for the universe to go was toward higher entropy, and it is this cosmic journey toward disorder that drives the forward march of time as we experience it. The expansion of the universe itself plays a crucial role, continuously creating new space and providing more room for particles to arrange themselves in increasingly disordered ways, ensuring that entropy has a vast and growing arena in which to increase. This thermodynamic arrow of time is not the only one we experience. It is intimately linked with two other arrows that define our reality. First, there is the cosmological arrow of time, defined by the expansion of the universe. The universe is getting bigger, and this expansion provides the direction for the thermodynamic arrow to play out. Second, and most personal, is the psychological arrow of time, our own perception of time's flow, our ability to remember the past and anticipate the future. It seems almost certain that our consciousness is tied to the thermodynamic processes in our brains. To form a new memory, your brain undergoes a physical change, a process that dissipates energy and increases entropy. You cannot have a memory of the future because that would require a decrease in entropy, a reversal of the very neural processes that make thought possible. Our minds, in a very real sense, are clocks powered by the universe's journey from order to disorder. The plot thickens considerably when we bring black holes into the picture. A black hole, by its very nature, possesses an immense amount of entropy. It is arguably the most disordered object possible for its size. When Stephen Hawking theorized that black holes could slowly evaporate by emitting radiation, he introduced a profound new layer to the puzzle of time. This Hawking radiation seems to cause a problem known as the black hole information paradox, which we will explore in depth later, but it also has implications for time's arrow. The process of a black hole forming from a collapsing star and then slowly evaporating over eons is a powerful, one-way process that drives entropy ever higher. It's a cosmic event that stamps a clear direction onto the fabric of space-time, reinforcing the idea that time's arrow is a consequence of the large-scale structure and contents of the universe, not a feature of its microscopic laws. Now, let's venture into a truly mind-bending theoretical possibility. In a hypothetical, isolated universe that is finite in size and contains a finite amount of matter, a mathematical concept called the Poincaré recurrence theorem suggests that given enough time, an almost unimaginably vast amount of time, every possible configuration of particles will eventually repeat. If you could wait long enough, the air molecules in your room would, by pure chance, all gather in one corner, leaving you gasping in a vacuum. If you could wait even longer, the entire universe could, in theory, spontaneously fluctuate back into a low entropy state similar to the Big Bang, effectively reversing the arrow of time for a fleeting moment before continuing its slide into disorder. This implies that in a closed, eternal universe, time's arrow might not be an absolute, unchanging constant. Yet, our observations show no evidence of such reversals. The universe appears to be on a relentless, one-way journey, its initial low-entropy state acting as a powerful anchor that sets the direction for all of cosmic history, making the recurrence time so astronomically long that it is, for all practical and philosophical purposes, infinite. This brings us to the deepest and most speculative layer of the riddle. What if our perception of time as a flowing river is, in some sense, an illusion? What if the past, present, and future all exist simultaneously in a static, block universe, as Einstein himself believed, and our conscious experience is merely a localized phenomenon, a cursor moving through this eternal structure? Or, even more radically, could the nature of time be different in other dimensions? In the complex geometries proposed by string theory, where extraspatial dimensions are compactified into tiny, curled-up shapes, could time itself behave differently? Could there be realms where the arrow of time points in a different direction, or where multiple arrows exist simultaneously, creating realities where cause and effect operate in ways our brains could never comprehend? If we could perceive these higher dimensional structures, would we see time not as a single line, but as a vast branching tree, or a multidimensional landscape where every possible history is real? How would that reshape our most fundamental experiences, our sense of self, our understanding of free will, and the very meaning of our lives, which are so deeply defined by the irreversible passage from birth to death? The enigma of time's arrow, therefore, is far more than a technical problem in physics. It is a gateway to understanding the connection between the cosmic and the conscious, and perhaps the ultimate clue that our reality is just one facet of a far richer, multidimensional existence. Picture this: you have a book, a thick volume filled with intricate stories and complex characters, and you decide to throw it into a blazing fire. The paper and ink are consumed, turning into heat, light, and smoke. According to the unshakable laws of quantum mechanics, that information, the specific arrangement of words that made that book unique, is not truly gone. In principle, if you could somehow collect every single ash particle, every photon of light, and trace the exact path of the heat, you could reverse the process and reconstruct the book perfectly. The information is preserved, just transformed. It is a foundational pillar of our understanding of the universe that information cannot be created or destroyed. It can only be scrambled. Now imagine throwing that same book into a black hole. According to Einstein's general relativity, the book would cross the event horizon, the point of no return, and be crushed into the central singularity, vanishing from our universe forever. The information it contained would be utterly and permanently erased. This is the heart of the black hole information paradox, a direct and violent collision between the two most successful theories in all of physics, and a puzzle that Stephen Hawking used to shake the foundations of theoretical physics for decades. Hawking's initial argument was as brilliant as it was troubling. He realized that black holes aren't completely black. Through a subtle quantum effect occurring right at the edge of the event horizon, they slowly emit a faint glow of radiation. A particle-antiparticle pair can pop into existence from the vacuum of space. If this happens right at the horizon, one particle can fall in while the other escapes, carrying away a tiny bit of the black hole's energy. This is Hawking radiation. The critical problem is that this radiation is purely thermal. It's random, featureless heat, like the glow from a hot stove. It contains no information whatsoever about what fell into the black hole. Whether you threw in a book, a star, or 1,000 elephants, the Hawking radiation coming out would be exactly the same. So when the black hole finally evaporates completely after eons, what happens to all the unique quantum information that described the original matter? If it is truly lost, then the fundamental principle of unitarity in quantum mechanics, the idea that the evolution of the universe is predictable and reversible, is fundamentally wrong. It would mean that the universe has a built-in mechanism for erasing its own history, rendering the future fundamentally unpredictable from the past. The implications of this are staggering. If information can be lost in a black hole, it undermines the very consistency of physics. Our ability to run the equations backward, to understand cause and effect, would break down at the event horizon. This conflict is so severe that it led to what is known as the Black Hole War among theoretical physicists, with Hawking on one side defending the idea of information loss and others like Leonard Susskind fiercely opposing it. Susskind and others argued that if quantum mechanics is correct, as countless experiments suggest, then there must be a way for the information to escape. As Susskind profoundly stated, black holes are not the end of information but a transformation we don't fully understand. The challenge was to explain how the information could get out, encoded in that seemingly random Hawking radiation, without violating the core tenets of relativity that say nothing can escape from behind the event horizon. This desperate search for a solution has given rise to some of the most mind-bending concepts in modern physics. One radical idea is the black hole firewall. If information is to be preserved, it might require that the event horizon is not the smooth, uneventful space that relativity predicts. Instead, it could be a blazing wall of high-energy particles, a literal firewall that instantly incinerates anything crossing it. This would protect the information by ensuring it never actually enters the black hole, but it would violently violate the equivalence principle, a cornerstone of general relativity which states that an observer falling into a black hole should feel nothing special as they cross the horizon. Another breathtaking proposal is the AR equals EPR conjecture, which links two seemingly unrelated ideas from Einstein's work. EPR refers to quantum entanglement, that spooky connection between particles. AR refers to Einstein-Rosen bridges, better known as wormholes. This idea suggests that two entangled particles might be connected by a microscopic wormhole. In the context of a black hole, the information about what fell in could be connected via these wormholes to the Hawking radiation that escaped, preserving the information in a highly non-local way, woven into the fabric of spacetime itself through a vast web of entanglement. Perhaps the most revolutionary framework for solving the paradox is the holographic principle, championed by Susskind and Gerard T. Hooft. This principle suggests that all the information contained within a volume of space can be thought of as encoded on its boundary, like a hologram on a two-dimensional surface. For a black hole, this means that all the information about every single thing that has ever fallen into it is not lost in the singularity, but is instead smeared and stored in tiny, Planck-sized units across the entire area of the event horizon. When Hawking radiation is emitted, it slowly and subtly reads out this information from the horizon, encoding it into the correlations between the radiation particles over time. The black hole, in this view, is the ultimate hard drive, with its information capacity proportional not to its volume, but to its surface area. This idea finds its most precise mathematical realization in the AD/S/CFT correspondence, a concept from string theory. It proposes a perfect duality between a gravitational theory in an anti-de Sitter space, a kind of universe with a negative cosmological constant, and a conformal field theory, a quantum theory without gravity that lives on its boundary. In this framework, a black hole in the bulk of space is equivalent to a hot, dense state of quantum matter on the boundary, and the information is always preserved in the boundary theory, resolving the paradox by changing our perspective on where reality truly happens. While testing these ideas against real black holes is currently beyond our reach, scientists have made remarkable progress using analog systems in laboratories. By creating sonic black holes or dumb holes in carefully controlled fluids like Bose-Einstein condensates, researchers can simulate an event horizon. In these setups, sound waves cannot escape from a region of fluid flowing faster than the speed of sound, creating an acoustic analog. By studying the quantum effects in these systems, particularly the analog of Hawking radiation, physicists hope to glean insights into whether information is preserved or lost in the process. Furthermore, the detections of gravitational waves by LIGO and Virgo from colliding black holes provide another, more indirect window. The specific ring-down signal after two black holes merge, the way they vibrate and settle into a new, single horizon, could potentially carry imprints of the information trapped within, or at least test the predictions of general relativity in these extreme regimes, guiding us toward the correct resolution. The relentless pursuit of an answer to the information paradox forces us to confront a truly fundamental question about the nature of reality. How can our two most powerful descriptions of the universe, general relativity and quantum mechanics, be so brilliantly successful in their own domains, and yet be fundamentally incompatible on this crucial point? The resolution will undoubtedly require a revolution in our thinking, perhaps one where the three-dimensional world we perceive is indeed a projection from a deeper, two-dimensional reality, or where space-time is fundamentally woven from quantum entanglement. Could it be that the missing information isn't lost at all, but is simply stored in a realm we cannot access, perhaps in the extra, compactified dimensions proposed by string theory, where the true degrees of freedom of nature reside? The black hole information paradox is more than a technical problem. It is a beacon guiding us toward a deeper union of the very large and the very small, and promising to reveal a layer of reality far stranger and more interconnected than we have ever dared to imagine. Look into the deepest, darkest patch of space you can find, a region between galaxies that seems utterly black and void. It's a natural assumption to think that this is nothingness in its purest form, a perfect and absolute emptiness. But that assumption, as modern physics has revealed, could not be further from the truth. What appears to our eyes as a vacant void is, in reality, a seething, bubbling, and wildly energetic ocean. At the tiniest of scales, at the level of the quantum, empty space is anything but empty. It is a dynamic frenzy where virtual particles and antiparticles spontaneously pop into existence, borrowing energy from the vacuum for an infinitesimally brief moment before annihilating each other and vanishing back into the ephemeral foam from which they came. This quantum jitter means that the vacuum of space possesses a fundamental energy, a background hum to the universe. The problem, the truly colossal problem, is that when physicists attempt to calculate the density of this vacuum energy using our well-tested theories of quantum fields, they arrive at a number of such staggering magnitude that it defies all reason. The theoretical prediction is a value that is 1 followed by 120 zeros times larger than the energy density we actually observe from the expansion of the cosmos. This isn't just a small rounding error or a minor miscalculation. This discrepancy of 10 to the 120th power is the single worst mismatch between theory and observation in the entire history of science. It is known quite appropriately as the vacuum catastrophe, and it stands as a glaring monument to the incompleteness of our understanding of the universe's most basic fabric. This catastrophic failure finds its historical roots in an idea from Albert Einstein himself. When he was first developing his theory of general relativity, he believed the universe was static and unchanging. His equations, however, kept predicting that a universe filled with matter should be either contracting under gravity or expanding. To force his model into a static state, he introduced a fudge factor, a term he called the cosmological constant, represented by the Greek letter lambda. This constant represented a repulsive force inherent to space itself, a kind of anti-gravity that could precisely balance the inward pull of matter, holding the cosmos in a steady state. When Edwin Hubble later discovered that the universe was indeed expanding, Einstein famously discarded his cosmological constant, reportedly calling it his greatest blunder. The irony is profound because decades later, with the discovery of the universe's accelerating expansion, the cosmological constant was resurrected. It is now the leading candidate to explain the dark energy that is driving galaxies apart at an ever-increasing rate. But this resurrection came with a devastating catch. The observed value of this cosmological constant, this energy of the vacuum, is not just a little small, it is inexplicably, preposterously tiny. As the Nobel Prize-winning physicist Steven Weinberg bluntly characterized it, the vacuum catastrophe is the most embarrassing problem in theoretical physics. It is a crisis that demands a radical shift, urging us to find new ideas that lie beyond the confines of our current quantum field theory. So, how could this unimaginable gap between prediction and reality possibly be bridged? Theorists have proposed several compelling, though still speculative, pathways. One elegant idea involves a concept known as supersymmetry. This theory proposes that every known fundamental particle has a hidden, super-partner particle that we have not yet discovered. For every electron, there would be a selectron, for every quark, a squark. The beautiful mathematical consequence of supersymmetry is that the contributions to the vacuum energy from ordinary particles and their superpartners would be exactly equal in magnitude but opposite in sign, causing them to perfectly cancel each other out, leaving a net vacuum energy of zero. This would solve the problem neatly. However, for this cancellation to be perfect, supersymmetry must be an unbroken symmetry of nature, meaning these partner particles would have to have the same mass as their standard counterparts. Our most powerful particle accelerators, like the Large Hadron Collider, have searched for these superpartners and have found no evidence of them. This suggests that if supersymmetry exists, it is a broken symmetry, meaning the partner particles are much heavier. While this broken version still offers some partial cancellation, it falls far short of resolving the catastrophic discrepancy, leaving the puzzle very much unsolved. Another fascinating possibility is that our universe is not in a true, stable vacuum, but is instead trapped in a metastable state. Imagine a vast, complex energy landscape with many valleys and hills. Our current vacuum state might be sitting in a very shallow valley, a local minimum that is stable for now, but not the absolute lowest possible energy state, the true vacuum. The energy of this local valley could correspond to the small, positive value we measure for dark energy. This is a precarious situation because it raises the terrifying possibility of a vacuum decay event. A quantum fluctuation could, in theory, cause our local patch of the universe to tunnel through the energy barrier and into the true, lower energy vacuum. This would not be an explosion in the traditional sense, but a wave of fundamental change that would sweep through the cosmos at the speed of light, rewriting the laws of physics in its wake. Atoms would disintegrate, forces would cease to function as they do, and all structure would be erased in an instant. The fact that this hasn't happened in 13.8 billion years suggests our metastable state is incredibly long-lived, but the mere possibility adds a dramatic tension to our cosmic existence. This line of thinking naturally connects to one of the most profound potential resolutions, the anthropic principle within a vast multiverse. If the string theory landscape is real, with its 10 to the 500 possible vacuum states, then every possible value of the cosmological constant is realized somewhere. In the overwhelming majority of these universes, the vacuum energy is enormous. In such places, the repulsive force would have been so powerful that it ripped space apart before any particles could even form, let alone coalesce into stars, planets, or living observers. We, quite obviously, do not find ourselves in one of those barren universes. We can only exist in one of the incredibly rare bubbles where the cosmological constant is almost, but not quite, zero, a value small enough to allow for billions of years of galaxy and star formation, yet large enough to eventually drive an accelerated expansion. In this view, the vacuum catastrophe is not a problem to be solved by a single equation, but a selection effect. We measure a small value for the vacuum energy because it is the only value compatible with our existence as conscious beings who can measure it. The universe is not fine-tuned for us. We are simply the products of a universe whose rare, accidental parameters allow for our kind of complexity. The precision of this fine-tuning is breathtakingly acute. If the vacuum energy were just a few dozen times larger than its observed value, its repulsive effect would have dominated the universe much earlier in cosmic history. The gentle gravitational tug of dark matter, which patiently pulls gas clouds together to form galaxies, would have been overwhelmed by this relentless push from within space itself. Proto-galactic clouds would have been blown apart before they could ever collapse. No galaxies, no stars, no planets would ever have formed. The universe would be a cold, dark, and ever-moored, dilute soup of isolated particles, forever devoid of structure or life. The fact that we live in a universe where this energy is so minuscule, yet crucially not zero, is what allows us to be here to ponder its existence. This forces us to confront a deeply philosophical question that straddles the line between physics and metaphysics. Why is the energy of nothingness so incredibly small, yet against all odds not exactly zero? What mechanism, what undiscovered symmetry or deeper layer of physical law is responsible for this seemingly miraculous cancellation? The answer may require us to look beyond our three familiar dimensions of space. It is conceivable that the vacuum energy we perceive and measure is not the full story. In theories with extraspatial dimensions, the true, fundamental vacuum energy could be as large as our quantum field theories predict. But its gravitational effects could be diluted or smeared out across these compactified, hidden dimensions that we cannot directly access. The tiny residual that leaks into our three-dimensional realm would then be the dark energy we observe. The vacuum catastrophe, therefore, might not be a failure of our mathematics, but a profound clue that we are only perceiving a fraction of the full, multidimensional reality. In the vast, silent expanse of the outer solar system, two robotic pioneers were quietly defying expectations. For decades after their launch in the early 1970s, the Pioneer 10 and 11 spacecraft continued their lonely journeys, hurtling toward the stars. But by the 1980s, a team of scientists led by John Anderson at NASA, a jet propulsion laboratory, noticed something deeply peculiar in the data. As they tracked the spacecraft using the faint whisper of their radio signals, they detected a consistent, tiny, and completely unanticipated drift. Both pioneers were experiencing a minute but constant deceleration back toward the Sun, a pull equivalent to just 10 billion times weaker than the gravity we feel on Earth's surface. It was as if a ghostly hand was gently applying the brakes, a force so small it should have been negligible, yet it persisted year after year, accumulating into a navigational mystery that simply could not be explained by the gravity of the sun and planets or by the gentle push of solar radiation. This was the birth of the Pioneer anomaly, a decades-long puzzle that would captivate and frustrate physicists, reminding everyone that even in the well-mapped territories of our own solar system, nature could still hold surprising secrets. The investigation into this subtle drift became a masterclass in meticulous, long-term scientific detective work. The primary tool was radio Doppler tracking. By measuring the precise frequency of the radio signal sent back to Earth by the spacecraft, scientists could determine their velocity with incredible accuracy. Any change in that frequency revealed a change in speed. It was through this method that the persistent blue shift in the Pioneer signals was discovered, indicating they were slowing down slightly more than all the known forces could account for. For years, exotic explanations flourished. Could it be the gravitational pull of unseen, dark matter clustered in our solar system? Was it evidence for a modification to Einstein's theory of general relativity, a new term in the equations of gravity that only became apparent over vast interplanetary distances? Some even speculated it was a hint of entirely new physics, perhaps related to the universe's expansion or the nature of the vacuum itself. The anomaly demonstrated a profound truth about exploration. Our most sensitive instruments are not just tools for confirming what we know, but probes for revealing the subtle flaws in our understanding. As John Anderson himself reflected, even small deviations in space missions can open doors to profound discoveries, reminding us that our models are incomplete. This tiny, unmodeled acceleration was a crack in the facade of classical celestial mechanics, and everyone wanted to see what lay behind it. The eventual resolution of the mystery is a story of patience and painstaking reconstruction. A large international team, led by Slava Tarishev, undertook a monumental effort to recover old data tapes and telemetry records, some of which were stored in a former McDonald's restaurant on the JPL campus. They pieced together the complete thermal history of the two spacecraft. The Pioneers were powered by radioactive thermoelectric generators, which produced heat as a byproduct of generating electricity. The team built a sophisticated thermal model of the spacecraft and realized that this heat was not radiating away perfectly symmetrically. More heat was being emitted from the back of the spacecraft's main dish antenna, which faced toward Earth, than from the front. This created a tiny but constant recoil force, a photon rocket effect where the photons of infrared radiation carrying heat away from the warmer rear side gave the spacecraft a minuscule push toward the sun. When this thermal recoil was finally and precisely quantified, it accounted for the vast majority of the anomalous acceleration. The ghostly hand, it turned out, was the gentle, asymmetric glow of the spacecraft's own warmth, a force that had been there all along, hidden in plain sight. Yet, even with this elegant thermal explanation, a sliver of the anomaly stubbornly remained. The modeled heat radiation did not perfectly cancel out the entire observed effect, leaving a tiny residual acceleration that is still not fully understood. This hints that there may be other, even subtler, forces at play, perhaps from the spacecraft's electrical systems or from gas leaks that were too small to be initially measured. The story of the Pioneer anomaly also finds echoes in other mysterious spacecraft behaviors. Consider the flyby anomaly, where spacecraft like Galileo, Near, and Rosetta experienced unexpected boosts in speed during gravity assist maneuvers around Earth. As these probes swung past our planet, their velocity increased slightly more than predicted by orbital dynamics. This speed boost is minuscule, mere millimeters per second, but it is another persistent deviation that has defied a single, universally accepted explanation. Some proposals suggest it could be linked to the Earth's rotation dragging space-time around it, an effect known as frame dragging, though the magnitude doesn't quite match. Others wonder if it points to unmodeled aspects of our planet's gravitational field or to subtle interactions with the tenuous outer atmosphere. These recurring puzzles, from the Pioneer's deceleration to the flyby's acceleration, tell a consistent story. When we push the boundaries of measurement precision, we often find that our maps of reality are not yet complete. The legacy of the Pioneer anomaly extends far beyond the fate of two aging spacecraft. It serves as a powerful reminder for missions designed to probe the fundamental nature of gravity and the unseen universe. When scientists plan experiments to detect dark matter or to test general relativity, they must now account for thermal effects with an unprecedented level of detail. The painstaking work that went into solving the Pioneer puzzle has made all of space science more rigorous. It has shown that to hear the faint whispers of new physics, we must first learn to silence all the known mundane noises. This pursuit of perfect precision is what drives the development of next-generation technologies, from more stable atomic clocks for deep space navigation to advanced laser interferometers that could one day detect the minute warping of spacetime by gravitational waves in the solar system. The quest to explain a tiny drift in two spacecraft has, in many ways, sharpened our tools for exploring the cosmos. So, where does this leave us? If most of the Pioneer anomaly has a conventional explanation, should we dismiss these tiny deviations as mere engineering curiosities? Or could they be something far more significant? What if these faint, residual anomalies are not flaws in our models, but the first subtle hints of a deeper layer of reality? Could the minuscule tugs and pushes on our spacecraft be evidence of subtle dimensional effects influencing gravity itself? In theories that propose extra-spatial dimensions, gravity could potentially leak into these hidden realms, causing it to behave in ways that differ slightly from the predictions of general relativity on certain scales. These effects would be incredibly small, exactly the kind of tiny, persistent signals that we might first detect as anomalies in the precise trajectories of deep space probes. The Pioneer's journey and the strange path of flyby spacecraft might be tracing out the invisible contours of a reality with more dimensions than we can see, a hidden architecture that only reveals itself through the most delicate of measurements. This curiosity about the smallest of deviations naturally propels us forward, transitioning our focus from the mysteries within our own solar system to the grand, speculative experiments that could one day test for the existence of these extra dimensions directly. It was a quiet, late summer night in Delaware, Ohio, and the Big Ear radio telescope was methodically scanning the sky, its massive parabolic reflector listening to the silent symphony of the cosmos. The date was August 15, 1977, and the telescope was part of a dedicated search for extraterrestrial intelligence, or SETI, program. The data was printed out on long, continuous sheets of paper, rows of letters and numbers representing the signal strength from different regions of space. A few days later, volunteer astronomer Jerry Amon was reviewing the printouts when his eye caught a sequence of characters so extraordinary that he circled it in red pen and, in a moment of pure, unguarded astonishment, scribbled a single, powerful word in the margin: "Wow." This wasn't just a minor blip. The signal, originating from the direction of the constellation Sagittarius, was a narrowband radio transmission that lasted for a full 72 seconds, the exact duration the Big Ear telescope could focus on a single point in the sky as the Earth rotated. It was incredibly strong, 30 times louder than the background noise of space, and it had a specific telltale fingerprint. It was concentrated around the frequency of 1420 MHz, a number that is profoundly significant in astronomy because it is the emission line of neutral hydrogen, the most common element in the universe. Many scientists had long suggested that this water hole in the radio spectrum would be a logical, universal channel for any advanced civilization trying to get noticed, a cosmic hailing frequency. The WOW signal fit this profile perfectly, a beacon that seemed to shout, "Here we are," into the void, and then, just as suddenly as it appeared, it vanished. Despite numerous and exhaustive attempts over the following decades to detect it again from the same location, the signal has never been heard. It remains a solitary, tantalizing data point, a cosmic siren call that faded back into the eternal silence, leaving behind one of the most enduring and compelling mysteries in the history of astronomy. The sheer uniqueness of the WOW signal forces us to seriously consider the spectrum of possibilities for its origin, from the mundane to the truly extraordinary. On the more conventional end of the scale, some scientists have proposed that it could have been a signal from a human-made object, such as a passing satellite or a piece of space debris reflecting our own transmissions back to us. However, the signal's specific frequency and its narrowband nature make this unlikely, as most human-made signals are broadband and would not have appeared so pristine on the printout. Another natural explanation that gained some traction was proposed in 2017, suggesting that the signal could have been caused by a comet. Two comets, in fact, were in the approximate area of the sky at the time, and they release large clouds of hydrogen gas that could potentially produce a radio emission. However, this hypothesis has been met with significant skepticism. Critics point out that the comets were not in the exact same beam of the telescope, and the specific frequency and intensity of the WOW signal don't perfectly match the known radio signature of cometary hydrogen clouds. The signal's transient, one-off nature also argues against a known, repeating cosmic phenomenon like a pulsar. This leaves the door open to more profound and frankly more thrilling interpretations. Could it have been a burst of communication from an interstellar spacecraft, a fleeting transmission as it passed through our neck of the galactic woods? Or, more monumentally, was it an intentional beacon from an advanced civilization, a brief, targeted hello that swept over our planet and then was gone, a message in a bottle cast into the ocean of space that we happened to catch at just the right moment? As the esteemed SETI researcher Jill Tarter has often reflected, the WOW signal is a powerful reminder that the cosmos is full of surprises, and we must keep listening with open minds. Her perspective captures the essence of the scientific spirit required for this search, one of patient optimism and relentless curiosity. The challenge, however, in pursuing this mystery is immense. Distinguishing an artificial, intelligent signal from the cacophony of natural cosmic noise is like trying to hear a single, unique instrument in a vast, chaotic symphony. The universe is filled with pulsars, quasars, and stellar flares that emit powerful radio waves. What made the WOW signal so special was its combination of being narrowband focused on one specific frequency, much like a radio station, and its intensity. Natural cosmic events tend to broadcast across a wide range of frequencies. The fact that it was never detected again is both frustrating and telling. If it was an intentional beacon, perhaps it was not meant to be continuous, but a periodic sweep across the galaxy, and we simply caught one brief pulse. Or perhaps it was a one-time event, a catastrophic explosion or a final, dying transmission from a civilization that flickered out. The failure to relocate it, despite many dedicated surveys of the same patch of sky, has only deepened the enigma, transforming it from a potential discovery into a permanent question mark. In the decades since that summer night, our methods for listening have grown exponentially more sophisticated. Modern SETI projects, like the monumental Breakthrough Listen Initiative, are using some of the world's most powerful radio telescopes, such as the Green Bank Telescope in West Virginia and the Parkes Observatory in Australia. These efforts employ advanced digital signal processing to scan billions of frequency channels simultaneously, looking for the faint, telltale signature of a technologically generated signal. They can filter out human-made interference with incredible precision and are systematically surveying 1 million nearby stars, the center of our galaxy, and even nearby galaxies. Breakthrough Listen has specifically re-scanned the region of the WOW signal with this modern arsenal, hoping to catch a repeat or a similar signal with far greater sensitivity. So far, the silence has held. This ongoing search highlights a fundamental shift. We are no longer just waiting for a lucky catch, but are conducting a comprehensive, technological census of our cosmic neighborhood, actively sifting through the static for a pattern that whispers of another mind. The story of the WOW signal, therefore, is not a closed case but an open invitation. It asks us to refine our technology, to expand our search strategies, and to remain perpetually vigilant. It fuels the development of next-generation telescopes, like the upcoming Square Kilometre Array, which will have the sensitivity to detect radar-like transmissions from planets orbiting nearby stars. The quest to find another WOW is driving us to become better, more attentive listeners in a universe that may be quietly and only occasionally trying to speak. This single, unexplained event leads us to a deeply personal and profound reflection. Was the WOW signal a genuine, fleeting hello from another civilization, a moment of cosmic contact that we were just advanced enough to receive but not yet sophisticated enough to understand or answer? The possibility ignites our imagination and challenges our perception of humanity's place in the cosmos. It forces us to ask how we can improve our methods, not just with better technology, but with smarter strategies. Perhaps we need to look for different kinds of signals altogether, not just radio, but laser optical communications, or even something more exotic that we haven't yet conceived. The enigma also invites a more speculative line of thought, one that connects back to the hidden layers of reality we've been exploring. Could it be that the reason we've never heard the signal again is not because the source is gone, but because the nature of the signal itself is tied to a physics we don't fully grasp? What if interstellar messages don't always travel in a straight line through our three-dimensional space? In theories involving extraspatial dimensions, the propagation of electromagnetic waves could be subtly altered, perhaps bent or focused in ways that create brief, intense hotspots of signal strength in certain locations, while leaving vast areas in silence. The WOW signal might have been a cosmic flashbulb going off, its light channeled through the hidden geometry of space-time, making it visible from Earth for just 72 seconds before the alignment shifted and the window closed. This idea transforms the signal from a mere message into a potential clue, a hint that to truly understand cosmic communication, we may first need to decipher the multidimensional fabric of the universe itself. We tend to imagine our position in the cosmos as utterly typical, a random speck in a vast, evenly sprinkled sea of galaxies. But what if our cosmic address isn't just average, but is actually situated in one of the grandest empty spaces we know? This is the startling perspective shift offered by the KBC void, a colossal bubble of relative emptiness, a staggering underdensity of galaxies spanning over 2 billion light-years across, with our own Milky Way located somewhere near its center. Picture a cosmic Swiss cheese on the most monumental scale imaginable, and we are living inside one of the holes. The very existence of this local void presents a direct challenge to a cornerstone of modern cosmology, the cosmological principle. This principle asserts that on sufficiently large scales, the universe should look roughly the same in all directions and from every location. It should be homogeneous and isotropic. The KBC void, named for astronomers Ryan Keenan, Amy Barger, and Lennox Cowie, who pieced together its evidence, suggests that on the scale of billions of light years, our universe might not be so uniform after all. This isn't just a curiosity, it's a potential crack in the foundation of our standard model of the cosmos, a model that relies on a smooth, even distribution of matter to explain everything from the Big Bang to the nature of dark energy. The discovery of this immense void wasn't the result of a single observation, but a painstaking synthesis of data from multiple galaxy surveys. By meticulously mapping the three-dimensional positions and densities of millions of galaxies, astronomers began to notice a puzzling pattern. In our immediate cosmic neighborhood, the number of galaxies per cubic megaparsec was significantly lower than the cosmic average. It was as if we were living in a vast, underpopulated rural area, while the true metropolitan centers of the universe lay far beyond our local bubble. This local hole isn't just an empty claim, it has tangible effects on how we measure the universe's expansion. The Hubble constant, which measures the current expansion rate of the universe, is calibrated using relatively nearby celestial objects like specific types of supernova. If we are sitting inside a giant void, the local gravitational landscape is different. The weaker gravity in our underdense region means that galaxies on the far side of the void are being pulled more strongly toward the denser regions outside of it, subtly affecting their apparent motion, and thus the local measurement of the expansion rate. This could be a key piece of the puzzle in explaining the Hubble tension, the troubling discrepancy between the measured expansion rate from the local universe and the value predicted from the early universe's afterglow. Perhaps our local measurement is slightly skewed because we are taking our cosmic senses from inside a grand emptiness. Theoretical cosmologist Laura Mersini-Horton has proposed a fascinating origin story for such vast structures. She suggests that the KBC void might not be a random fluctuation, but rather a fossilized imprint from the universe's very first moments. Voids like this could be fossils of primordial physics, she has said, pointing to the quantum fluctuations that were stretched to cosmic proportions during the period of inflation. In this view, the tiny, random ripples in the Inflaton field that seeded all cosmic structure didn't just create the dense knots that became galaxy clusters, they also created the vast, underdense troughs that became great voids. Our local cosmic emptiness, then, could be a direct link to the quantum nature of reality itself, a macroscopic relic of the universe's microscopic birth. This idea elevates the void from a mere curiosity to a potential window into physics at the highest energies, a fossil waiting to be decoded. The plot of our local cosmic geography thickens even further when we consider the forces not just pulling us but also pushing us. Astronomers have identified a region they call the dipole repeller. While the Great Attractor and the Shapley supercluster are massive concentrations of matter pulling our galaxy and its neighbors in their direction, the dipole repeller is essentially the opposite, a vast, underdense region whose lack of gravitational pull effectively acts as a repulsive force pushing galaxies away from it. Think of it like a landscape where you are sliding downhill. The dense superclusters are the deep valleys pulling you in, but the voids are the high plateaus you are sliding away from. The motion of our local group of galaxies is thus a complex interplay between being pulled toward the dense Shapley supercluster and pushed away from the empty dipole repeller and our own KBC void. This complex gravitational dance reveals a universe that is far more structured and dynamic on large scales than a simple, smooth expansion would suggest. Understanding how these voids evolve over time is crucial to this story. In the early universe, underdensities were only slightly less dense than the average. But as the cosmos expanded, gravity played its relentless role. Matter flowed out of these underdense regions and into the surrounding, slightly denser filaments and walls of the cosmic web. This process, known as void evacuation, left behind ever larger and emptier bubbles over billions of years. The KBC void is likely a mature example of this process, a cavern that has been growing and emptying out for most of cosmic history. The galaxies that do remain inside it are like isolated islands in an ever-widening ocean, their fates shaped by the large-scale emptiness that surrounds them. This evolution is not just a sideshow, it is an integral part of how the cosmic web builds itself, with voids making up the majority of the volume of the universe. They are not just empty space, but active participants in the cosmic drama, their expansion and evolution influencing the development of the dense structures that define the visible universe. So we are left to ponder a question that is both simple and deeply profound. Why is our cosmic backyard so remarkably empty? Is the KBC void simply a statistical fluke, a rare but inevitable low point in the random distribution of matter, and we just happen to be here to observe it? Or does its immense scale and our central location within it point to something more fundamental? Could it be evidence that the cosmological principle, while a useful approximation, breaks down on scales larger than we previously thought? The existence of such a vast structure forces us to reconsider the very texture of the cosmos, and this line of inquiry naturally leads to a more speculative but thrilling possibility. What if the large-scale inhomogeneities we see, the great voids and superclusters, are not just the result of random quantum fluctuations in 3 dimensions? In theories that involve extraspatial dimensions, the fabric of spacetime itself could have inherent variations or wrinkles that originated from the way those dimensions were compactified and stabilized in the earliest moments. The gravitational influence of these hidden dimensional geometries could have imprinted preferred underdensities and overdensities on our 3-dimensional universe, creating a cosmic web whose pattern we are only now beginning to trace. The KBC void, then, might be more than a fossil of quantum physics. It could be a shadow cast by the hidden architecture of reality, a clue that the true structure of the cosmos is written in more than 3 dimensions. Imagine the ultimate baby picture of the universe, the cosmic microwave background, a snapshot of the cosmos when it was just a newborn. We expect this image to be a random, almost featureless tapestry, a testament to a universe that is fundamentally the same in all directions, a principle that has guided cosmology for generations. But then you look closer and something unsettling emerges. The largest scale patterns in this ancient light, the very first ripples of creation, appear to be subtly aligned. Their orientation isn't random. It seems to correlate with the plane of our own solar system, a direction so improbably linked to our local cosmic address that scientists half-jokingly, half-seriously dubbed it the axis of evil. This isn't a name from a science fiction movie. It's a label born from the profound discomfort this alignment causes. The implication is staggering. It suggests that our privileged position as observers might somehow be imprinted on the universe's oldest light, either revealing a fundamental flaw in our observations or, far more excitingly, a crack in one of our most cherished cosmological principles. This startling discovery was first brought into sharp focus by cosmologists Kate Land and Joe Megiddo in the early 2000s. By analyzing data from NAS, a Wilkinson microwave anisotropy probe, they noticed that the largest temperature fluctuations in the CMB weren't randomly scattered. Specifically, they found that the quadrupole and octupole moments, which describe the largest and most fundamental wiggles in the background radiation, were unusually aligned with each other and, even more bizarrely, with the ecliptic plane, the path the Sun and planets trace across our sky. This is the cosmic equivalent of finding that the brushstrokes on a vast, ancient canvas are all pointing toward the spot where you happen to be standing. It challenges the very notion of isotropy, the idea that the universe has no preferred direction or center. If this alignment is real and not an illusion, it means the cosmos might have a built-in orientation, a cosmic north that upends our assumption that we live in a perfectly uniform, democratic universe. As the renowned physicist Max Tegmark has wisely noted, anomalies like this keep cosmologists humble, as they might point to revolutions in our understanding. The axis of evil is precisely this kind of humbling puzzle. It forces us to question whether we are seeing the universe as it truly is, or if our view is being distorted by a lens we haven't yet identified. The investigation into this anomaly has unfolded like a high-stakes forensic audit of the cosmos. Scientists have scrutinized every possible source of contamination. Could it be foreground pollution from dust within our own Milky Way galaxy? Could it be an unaccounted-for signal from the solar system itself, perhaps the faint glow of charged particles in its magnetic field? The European Space Agency's Planck satellite, which provided the most detailed and precise map of the CMB ever created, was tasked with answering this very question. After painstakingly modeling and subtracting every known source of interference, from galactic synchrotron radiation to interstellar dust, the Planck team confirmed that the anomalous alignment stubbornly persisted, though its statistical significance was reduced. It didn't go away, but it became a fainter, more ambiguous whisper, leaving the community divided on whether it was a ghost in the machine or a genuine feature of the primordial universe. This ambiguity has opened the door to a spectrum of theoretical explanations, each more mind-bending than the last. One fascinating possibility involves the overall topology of the universe. What if the cosmos isn't infinite and flat, but has a finite, multiply-connected shape, like a hall of mirrors or a video game screen that wraps around on itself? In such a universe, light could travel along multiple paths, creating repeating patterns and large-scale correlations that might appear as strange alignments to an observer inside the structure. The axis of evil could be the first hint that our universe has a global geometry we have yet to map. Another compelling, though highly speculative, idea connects the anomaly to the multiverse. If our universe is just one bubble in a vast cosmic foam, then the violent process of bubble nucleation and collision in the early moments of inflation could have imparted a specific directional preference to our local patch of spacetime. The alignment we see would then be a cosmic scar, a permanent reminder that we are not alone in the greater meta-universe, but part of a family of universes, each with its own unique birthmarks. Beyond these exotic proposals, the anomaly also fuels the search for primordial gravitational waves. These ripples in spacetime, generated during the inflationary epoch, would have left a distinct swirling pattern in the polarization of the CMB, known as B-mode polarization. Some theorists suggest that the same physical mechanism that produced the axis of evil alignment could also have generated a specific, directional pattern in these gravitational waves. While the current hunt for primordial B-modes has been fraught with challenges, primarily due to contamination from interstellar dust, the potential link to the axis of evil adds another layer of motivation to this monumental effort. Finding a correlated signal would transform the anomaly from a curious statistical fluke into a powerful new probe of physics at the highest energies. So we are left standing at a scientific crossroads. facing a question that cuts to the core of our cosmological models. Is the axis of evil merely a persistent statistical fluke, a grand cosmic coincidence that will eventually fade away with more precise data? Or is it the first, faint glimpse of a deeper layer of cosmic architecture, a fundamental preferred direction woven into the fabric of reality? The answer holds profound consequences. If confirmed, it would mean that the universe is not isotropic on its very largest scales. It would force a rewrite of our standard model of cosmology and challenge the Copernican principle that we do not occupy a special place in the cosmos. This line of inquiry inevitably draws our curiosity toward the very structure of space itself. Could it be that the presence of hidden, compactified dimensions, as proposed by string theory, is the ultimate source of this cosmic orientation? If our three-dimensional space is embedded within a higher dimensional bulk, the geometry and dynamics of those extra dimensions could naturally break the perfect symmetry of our observable universe, introducing a subtle but pervasive directional preference that manifests in the oldest light we can see. The axis of evil, therefore, might not be a flaw at all, but a luminous signpost pointing directly toward the hidden, multidimensional foundations of everything we know. At the heart of modern cosmology lies a fundamental number, a single value that dictates the pace of cosmic evolution and ultimately the fate of everything we see, the Hubble constant. It is the universe's current expansion rate, a measure of how fast galaxies are receding from us for every megaparsec of distance. For decades, we've been refining our methods to pin down this number with ever greater precision, expecting that different techniques would eventually converge on a single, universal truth. Instead, we've stumbled into a crisis. When we measure the expansion rate using the ancient light from the cosmic microwave background, the afterglow of the Big Bang, we get one answer. But when we measure it using relatively nearby stars and supernova, we get a different one. The two values disagree by a small but stubborn and significant amount, roughly 10%. This isn't a minor statistical wobble. It's a glaring, persistent discrepancy that has ballooned into the most pressing problem in cosmology, known as the Hubble tension. It's as if you used two different, impeccably calibrated rulers to measure the same object, and each one gave you a definitively different length. This conflict suggests that something is profoundly wrong, either with our measurements or, far more excitingly, with our foundational understanding of the universe itself. The two sides of this cosmic standoff are represented by two of the most powerful tools in astronomy. On one side, we have the Planck satellite, which mapped the cosmic microwave background with exquisite detail. By analyzing the subtle patterns of hot and cold spots in this primordial light, cosmologists can work backward through the entire history of the universe, using our well-established model of cosmic evolution, the lambda cold dark matter model, to predict what the expansion rate should be today. This early universe method yields a Hubble constant of about 67 kilometers per second per megaparsec. On the other side is the SH0ES team, led by Nobel laureate Adam Rees, who use a distance ladder built from observations within our local universe. They start with pulsating stars called Cepheid variables in our own galaxy, whose known relationship between pulsation period and intrinsic brightness makes them superb standard candles. They then use these Cepheids to calibrate the distances to galaxies that host another type of standard candle, the brilliant type Ia supernova. By measuring how fast these galaxies are moving away from us, they arrive at a Hubble constant of around 73. The gap between these two values might seem small, but given the incredible precision of both methods, it is a chasm. As Rees himself has powerfully stated, the Hubble tension is a crack in the cosmological model, and through it we might see a new reality. This isn't just a technical disagreement, It is a potential gateway to discovering physics beyond our current standard model. The persistence of this tension has forced cosmologists to scrutinize every possible source of error, from tiny miscalibrations in the distance ladder to subtle systematic biases in the CMB data. Yet, as the measurements have become more precise, the discrepancy has only hardened, ruling out simple observational mistakes. This has opened the floodgates to a wave of theoretical speculation, with physicists proposing exotic new ingredients or modifications to our cosmic recipe. One of the most compelling ideas is the concept of early dark energy. Our current model assumes that dark energy, the mysterious force driving cosmic acceleration, has been constant throughout time. But what if it wasn't? What if, in the very early universe, there was a brief, additional burst of this repulsive energy that altered the sound horizon, a fundamental ruler imprinted on the CMB? This early burst would change the interpretation of the Planck data, leading to a higher predicted value for today's Hubble constant, potentially bringing it into line with the local measurements. It would be as if the universe had a rebellious teenage phase of extra rapid expansion before settling into its current, more sedate acceleration. Another fascinating avenue involves the ghostly particles known as neutrinos. The standard model of particle physics treats neutrinos as nearly massless, but we now know they have a tiny, non-zero mass. What if they are slightly heavier, or if there exists a new, sterile variety of neutrino that interacts only through gravity? These additional neutrino properties could have subtly influenced the rate at which cosmic structures formed in the early universe, again tweaking the calibration from the CMB to the present day. The properties of dark matter itself are also under scrutiny. Perhaps dark matter interacts with itself or with normal matter in ways we haven't accounted for, creating friction or pressure that altered the cosmic expansion history. These are not wild guesses, they are calculated adjustments to a model that has been spectacularly successful in so many other ways, demonstrating how a single, stubborn anomaly can drive a whole field toward innovation. Beyond these grand theories, astronomers are also developing entirely new methods to measure the Hubble constant, hoping to break the deadlock. One particularly elegant technique involves gravitational lensing time delays. When a massive foreground galaxy cluster bends the light from a more distant quasar, it can create multiple images of that quasar. Because the light for each image takes a slightly different path around the lens, they arrive at Earth at different times. By carefully monitoring the flickering of these images and modeling the mass distribution of the lensing cluster, scientists can directly triangulate the distance to the system, providing a completely independent route to the Hubble constant that bypasses both the CMB and the traditional distance ladder. Intriguingly, some of these lensing measurements have landed in the middle of the dispute, neither fully supporting the early nor the local value, adding another layer of intrigue to the puzzle. This proliferation of methods highlights the creative fervor this tension has ignited, as the entire community rallies to solve a problem that strikes at the very core of our cosmic narrative. The implications of this dispute extend far beyond a simple number. The Hubble constant is inextricably linked to the age of the universe. A faster expansion rate implies a younger cosmos, while a slower rate suggests an older one. The current tension translates to a difference of over 1 billion years in the estimated age of the universe. Furthermore, the expansion rate dictates the future. It tells us how the tug of war between dark energy and gravity will ultimately play out, influencing predictions about the long-term fate of all cosmic structure. Resolving the Hubble tension is therefore not an academic exercise. It is about getting the timeline of cosmic history correct and accurately forecasting the destiny of everything. This leads us to a pivotal and deeply unsettling question. Why, with all our technological prowess and theoretical sophistication, can we not agree on how fast the very space we inhabit is growing? What hidden factors, what subtle threads in the fabric of reality are we failing to account for in our equations? The answer may require us to look beyond the familiar three dimensions of space. It is conceivable that the presence of compactified extra dimensions, as suggested by string theory, could be subtly influencing the global geometry of the universe and the behavior of gravity on the largest scales. If gravity were to leak slightly into these hidden realms over cosmic distances, it could alter the apparent expansion rate we measure, creating a discrepancy that depends on whether we are looking at the local universe or the vast, ancient scales of the CMB. The Hubble tension, therefore, might be the first observable tremor from a hidden dimensional landscape, a faint signal that our reality is embedded within a far grander, multidimensional architecture. Now let's dive into one of the most conceptually challenging riddles, a phenomenon that forces us to question the very nature of what is real and what is an illusion depending on how we move. Picture an astronaut floating in the deep, cold void of what appears to be completely empty space. To all their instruments and to any other astronaut floating alongside them, this vacuum is just that, a silent, particle-free nothingness. But now, imagine our astronaut fires up a powerful rocket pack and begins to accelerate faster and faster. From their new, accelerating perspective, something miraculous and bizarre happens. The once silent void begins to glow. Their particle detector, which moments ago registered nothing, suddenly clicks to life, registering a warm bath of real particles and heat. This is not a malfunction. This is the Unra effect, a stunning prediction of quantum field theory that tells us an accelerating observer will perceive the vacuum of space not as empty, but as a thermal sauna filled with radiation. The vacuum itself has a temperature, but only if you're accelerating through it. Proposed by physicist Bill Unra in 1976, this effect creates a profound and intimate link between acceleration and temperature, suggesting that the very concept of a particle is not absolute, but depends entirely on your state of motion. It blurs the line between the twin pillars of modern physics, Einstein's relativity and quantum mechanics, by showing that what one observer sees as empty space, another sees as a populated, energetic arena. The mechanics behind this illusion, or rather, this shift in reality, are rooted in the strange, fluid nature of the quantum vacuum. According to quantum field theory, what we call empty space is not truly empty. It is a seething, dynamic foam where virtual particle-antiparticle pairs constantly flicker in and out of existence. For an observer moving at a constant velocity, these fleeting fluctuations remain virtual and undetectable. However, for an observer who is accelerating, this serene picture changes dramatically. The act of acceleration creates a horizon, a boundary in space beyond which information cannot reach the observer, much like the event horizon of a black hole. This horizon disturbs the delicate balance of the quantum foam. Some of those virtual particles, which would normally annihilate each other and vanish, get separated by the horizon. One particle falls behind while its partner is ripped away and becomes a real, detectable particle from the accelerating observer's point of view. These particles appear to the observer as a perfectly thermal bath of radiation, with a temperature that is directly proportional to their acceleration. The faster you accelerate, the hotter the vacuum around you appears to become. The formula is startlingly simple. The temperature is equal to your acceleration multiplied by a very small number, Planck's constant, and divided by the speed of light and other constants. While the concept is elegant, the numbers are forbidding. To experience a vacuum temperature of even 1 degree above absolute zero, you would need an acceleration of a quadrillion meters per second squared, an acceleration far, far beyond anything our current technology can produce, a level of force that would instantly crush any known material or organism. This bizarre effect is not an isolated curiosity. It is deeply intertwined with one of the most famous predictions in all of physics: Hawking radiation from black holes. Stephen Hawking calculated that black holes are not completely black, but slowly evaporate by emitting thermal radiation. The mechanism is eerily similar to the Unra effect. For a hypothetical observer falling into a black hole, the vacuum near the event horizon appears empty, but for a distant observer sitting safely far away, that same vacuum is teeming with a thermal glow Hawking radiation. The gravitational pull of the black hole effectively plays the role of the acceleration in the Unra effect. This deep connection suggests a universal principle. Horizons, whether created by acceleration or by gravity, heat up the quantum vacuum and transform our perception of reality. As the renowned physicist Leonard Susskind has insightfully noted, effects like Unra remind us that reality depends on the observer, challenging absolute truths. There is no single, God's-eye view of what particles exist in a given region of space. Your reality is fundamentally tied to your own motion and perspective. The immense challenge of directly detecting the Unra effect has not stopped physicists from devising incredibly clever, albeit indirect, ways to test its validity. One promising avenue involves using the tremendous accelerations experienced by electrons in ultra-intense laser fields. When electrons are subjected to the oscillating fields of a powerful laser, they can be whipped back and forth at accelerations approaching the required levels. While detecting the emitted Unra radiation directly amidst the blinding glare of the laser is still fantastically difficult, scientists are looking for subtle signatures in the way these electrons behave, or in the specific spectrum of light they might emit as a consequence of bathing in this perceived thermal bath. Other proposals are even more inventive, suggesting that certain superconducting systems or Bose-Einstein condensates could be engineered to simulate the conditions of an accelerating observer, allowing us to study the Unra effect in a controlled laboratory setting. These analog experiments are crucial testing grounds, providing hints about the underlying quantum field theory without needing to achieve astronomical accelerations. The implications of the Unra effect ripple out to touch one of the most sacred principles in physics, Einstein's equivalence principle. This principle states that the effects of gravity are locally indistinguishable from the effects of acceleration. If you are in a closed box, you cannot tell whether you are sitting on the surface of the Earth or being accelerated through space in a rocket. The Unra effect adds a fascinating and complex layer to this idea. It suggests that an accelerated observer will see a thermal environment. By the equivalence principle, this implies that an observer at rest in a gravitational field should also see a thermal environment. This is exactly what happens with Hawking radiation. So, the Unra effect provides a beautiful, conceptual bridge between acceleration and gravity, reinforcing their deep connection and hinting that thermodynamics and the nature of heat are not just emergent properties of matter, but are fundamentally woven into the geometric fabric of spacetime itself. If the Unra effect is experimentally verified, it would provide powerful, indirect support for the reality of Hawking radiation and bolster various approaches to quantum gravity that rely on these thermodynamic analogies. This leads us to a truly mind-bending reflection on perception and reality. How does our simple motion through the cosmos actively alter the very particles and forces we perceive around us? The Unra effect demonstrates that the universe is not a static stage on which we are passive actors. Our movement writes the script determining which characters, which particles, appear in our local play. This profound observer dependence forces us to abandon any naive notion of an objective, external reality that is the same for everyone, and this, in turn, opens the door to an even more speculative possibility. Could the strength of the Unra effect, or the very nature of the quantum vacuum it reveals, be different in a universe with more than 3 spatial dimensions? In theories with compactified extra dimensions, the properties of the quantum fields that fill space could be altered. The spectrum of virtual particles might be different, and the way they respond to an accelerating observer could be amplified or modified. An observer accelerating in a higher dimensional bulk might perceive a vacuum temperature far greater than what our 3-dimensional equations predict, or detect a different kind of radiation altogether. The Unra effect, therefore, is not just a quantum curiosity. It is a potential probe, a sensitive instrument that could one day reveal how our observable physics is just a 3-dimensional shadow of a richer, multidimensional reality, where motion through hidden realms fundamentally changes the world we see. Think about the forces that shape your daily life. When you use a magnet to stick a note to your fridge, you are effortlessly overcoming the gravitational pull of the entire planet Earth. That simple act highlights one of the most baffling imbalances in all of nature. Gravity is phenomenally, almost incomprehensibly, weaker than the other fundamental forces. To be precise, the gravitational attraction between 2 particles is about 10 to the power of 36 times weaker than the electromagnetic force pushing them apart. This isn't a small difference, it's a number so vast that it defies easy analogy. It's like comparing the strength of a single person to the combined might of 1 billion, trillion people. This staggering disparity is known as the hierarchy problem. And it's not just a curiosity, it's a fundamental crisis for our understanding of the universe, because our best theories suggest that gravity shouldn't be this weak at all. The heart of the problem lies in the quantum world, and specifically with the Higgs field, the invisible energy field that gives particles their mass. The mass of the Higgs boson itself is precariously balanced. In the quantum frenzy of the vacuum, virtual particles of incredibly high energy constantly pop in and out of existence. These fleeting fluctuations should interact with the Higgs field and drive its expected mass up to a scale quadrillions of times heavier than what we actually observe, a scale known as the Planck scale, where gravity becomes as strong as the other forces. For the Higgs mass to remain at the relatively low value we measure, it requires an exquisitely fine-tuned cancellation between these enormous quantum corrections, a cancellation that seems as unlikely as perfectly balancing a pencil on its tip during an earthquake. This unnatural fine-tuning suggests that our standard model of particle physics is incomplete. There must be some new physics, some hidden mechanism or symmetry, that naturally protects the Higgs mass and explains why the force of gravity feels so feeble in our everyday world. One of the most elegant proposed solutions is a concept known as supersymmetry. This theory posits that every known fundamental particle has a hidden super-partner particle. For every electron, there would be a selectron, for every quark, a squark. The profound beauty of supersymmetry is that the quantum contributions from these superpartners would perfectly cancel out the enormous corrections from their standard counterparts, naturally stabilizing the Higgs mass at its observed low value and resolving the hierarchy problem in one graceful stroke. For decades, physicists hoped that the Large Hadron Collider would discover this symmetrical world. However, after years of smashing protons together at unprecedented energies and scrutinizing the debris, no evidence for these superpartners has emerged. Their continued absence suggests that if supersymmetry exists, it is a broken symmetry, meaning the partner particles are far heavier than initially hoped, and the perfect cancellation is spoiled, leaving the fine-tuning problem largely unsolved and pushing this beautiful idea into a more constrained and challenging theoretical space. Faced with this challenge, other physicists have taken a radically different approach, one that turns the problem on its head. What if gravity isn't inherently weak? What if it only appears weak to us because we are trapped in a three-dimensional reality, unable to perceive the full extent of its influence? This is the breathtaking premise of the large extra dimensions theory, most famously proposed by physicists Nima Arkani-Hamed, Savas Dimopoulos, and Gia de Valle. They argue that the hierarchy might not be a problem but a clue to the structure of spacetime. In their vision, our entire universe of three spatial dimensions could be a membrane, or brain, floating within a higher dimensional bulk. Crucially, the particles of the standard model, the building blocks of matter and light, might be stuck on our brain, unable to leave. Gravity, however, as the geometry of spacetime itself, could be the only force that permeates all dimensions. Imagine our three-dimensional space as the surface of a vast, taut trampoline. We and everything we see are like tiny ants confined to that surface. The other fundamental forces, like electromagnetism, are like glue that only works on the trampoline's fabric. Gravity, however, is like a ripple that can travel not just across the surface, but also through the thick padding beneath it. If there are large, compactified extra dimensions, the gravitational field generated by matter on our brain would spread out into this larger volume. From our perspective on the brain, the force of gravity would be dramatically diluted, explaining its apparent feebleness. The strength we measure wouldn't be gravity's true strength. It would just be a faint shadow of its full power, a diluted signal leaking into our dimensional prison. In this scenario, the true Planck scale, where gravity becomes strong, could be much lower, even as accessible as the energies probed by the LHC, completely eliminating the need for any fine-tuning and offering a dramatic geometric explanation for the hierarchy. This brainworld hypothesis leads to another stunning possibility: the existence of miniature black holes. If the Large Hadron Collider could ever reach energies high enough to probe the true, stronger scale of gravity in the bulk, it might not just discover new particles, it could actually create microscopic black holes. These wouldn't be the cosmic monsters that swallow stars. They would be tiny, ephemeral objects that would evaporate almost instantly via Hawking radiation, leaving behind a unique and unmistakable signature in the detector. While the LHC has not yet seen any signs of these mini black holes, their potential discovery remains one of the most thrilling and direct ways to test for the existence of large extra dimensions. Beyond supersymmetry and extra dimensions, a third profound solution emerges from the concept of the multiverse and the anthropic principle. If our universe is just one of a vast, perhaps infinite, number of universes in a multiverse, each with different physical constants and laws, then the hierarchy problem changes from a why to a where. In the overwhelming majority of these universes, the Higgs mass might be at the enormous Planck scale. In such a cosmos, gravity would be as strong as the other forces from the very beginning. This would have catastrophic consequences for the emergence of complexity. Stars would be tiny, short-lived objects, planets could not form in stable orbits, and the intricate chemical processes necessary for life would be impossible. We, as conscious observers, could only ever find ourselves in one of the incredibly rare universes where a random, accidental cancellation has occurred, setting the weak scale and the strength of gravity to the precise values that allow for galaxies, stars, planets, and ultimately, life to evolve. In this view, the hierarchy isn't a problem to be solved by a single equation, but a consequence of our own existence as observers in a bio-friendly bubble of the cosmos. This grand puzzle is inextricably linked to the other great mystery we've explored, the vacuum catastrophe. The same quantum corrections that threaten to make the Higgs mass enormous also contribute to the vacuum energy of empty space. A solution to the hierarchy problem, whether through supersymmetry, extra dimensions, or another mechanism, would also have to address why the energy of the vacuum is so close to zero. It's a reminder that these cosmic riddles are not isolated. They are deeply interconnected, each one a different thread in the same magnificent tapestry of physical law. The ongoing search for answers continues to drive the design of ever more powerful particle colliders and inspires the development of exquisitely sensitive experiments to measure the force of gravity at microscopic distances, where the influence of hidden dimensions might finally become detectable. So we are left with a question that challenges our most basic assumptions about reality. Why does the force that holds planets, stars, and galaxies together feel so insignificant in our local world? Is its apparent weakness a clever illusion, a geometric effect of gravity spreading its influence into dimensions hidden from our view? The answer will not only reveal why our universe is structured the way it is, but could also unveil the true, multidimensional architecture of spacetime itself. But to truly understand the universe's first moments, we must listen not just for light, but for a far more elusive whisper. Imagine a hidden world, a cosmic fossil record that has been streaming through the universe and through your own body since the cosmos was just 1 second old. This isn't a metaphor, it's the cosmic neutrino background, a vast sea of relic particles that is arguably the next great frontier in observational cosmology. In the fiery chaos just after the Big Bang, the universe was a dense, opaque soup of particles, with light trapped in a constant dance with electrons and protons. But roughly 1 second after it all began, the universe had expanded and cooled just enough for a pivotal event to occur. Neutrinos, those famously ghostly and nearly massless particles, ceased their constant interactions with other matter. They decoupled, flying freely through the suddenly transparent universe, never to be significantly disturbed again. This moment created a snapshot, a background radiation of neutrinos that has been cooling and spreading with the expanding cosmos ever since, a perfect counterpart to the cosmic microwave background that formed hundreds of thousands of years later. While we have mapped the CMB with stunning precision, this cosmic neutrino background remains the last major prediction of the Big Bang model that has not been directly detected. It is a pristine messenger from the universe's very first second, holding within its subtle properties the answers to questions that have puzzled physicists for generations. These relic neutrinos are not passive travelers, they are dynamic actors in the cosmic story, their ghostly presence influencing the very formation of the large-scale structures we see today. Because they decoupled so early and travel at velocities incredibly close to the speed of light, they streamed freely out of overdense regions in the early universe. This streaming acted like a kind of cosmic pressure, smoothing out the primordial lumps and bumps and effectively putting the brakes on the gravitational collapse that forms galaxies and clusters. The gravitational tug-of-war between dark matter's pull and the neutrino's push left a specific imprint on the distribution of matter. The presence of these light, fast-moving particles suppressed the growth of the very smallest cosmic structures. This means that by meticulously mapping the clustering patterns of millions of galaxies across the sky, astronomers can indirectly sense the presence and properties of the cosmic neutrino background. The effect is subtle, but it's there, a faint signature in the cosmic web that tells us these particles are real and that they have a small but non-zero mass. In fact, these observations from galaxy surveys provide some of the tightest constraints we have on the sum of the masses of all 3 known types of neutrinos. They tell us that neutrinos are incredibly light, millions of times lighter than an electron, but that their collective gravitational influence, spread across the vast sea of the cosmic neutrino background, has subtly sculpted the cosmos for over 13 billion years. The quest to move from this indirect evidence to a direct, unambiguous detection of a single relic neutrino is one of the most formidable challenges in modern experimental physics. The core of the problem lies in the neutrino's infamous nature. It interacts only via the weak nuclear force and gravity. A relic neutrino from the Big Bang has incredibly low energy today after being cooled by the universe's expansion for so long. To have any hope of capturing one, a detector must be unimaginably massive and placed in an environment of profound silence, shielded from the relentless cacophony of cosmic rays and natural radioactivity. One of the most promising projects on the horizon is the Ptolemy experiment, which stands for the Princeton Tritium Observatory for Light Early Universe Massive Neutrino Yield. The proposed design is a masterpiece of ambition. It would use a 100-gram target of tritium, a radioactive form of hydrogen. The idea is to catch a relic neutrino through a process called inverse beta decay. If a low-energy relic neutrino were to interact with a tritium nucleus, it would transform a neutron into a proton and kick out an electron with a very specific telltale energy signature. The challenge is monumental. The expected signal is vanishingly small, a handful of events per year buried in a sea of background noise from other processes. Isolating that signal is like trying to hear a single, specific whisper in a roaring stadium during a hurricane. It will require technological marvels in cryogenics, ultra-pure materials, and signal processing that push the very limits of our engineering capabilities. Beyond their role in structure formation, these relic neutrinos were also key players in one of the universe's first chemical transformations, Big Bang nucleosynthesis. In the first 3 minutes, the cosmos was a nuclear fusion reactor, fusing protons and neutrons into the first light elements deuterium, helium, and a tiny bit of lithium. The rate of this fusion was exquisitely sensitive to how fast the universe was expanding at the time, and the expansion rate, in turn, was governed by the total density of all relativistic particles, those moving near the speed of light. The cosmic neutrino background, with its 3 known flavors, contributed significantly to this energy density, effectively turning up the heat and speeding up the expansion. This faster expansion shortened the window of time available for nuclear reactions to occur, leaving a specific fingerprint on the final abundances of these primordial elements. The fact that our observations of deuterium and helium in the universe match the predictions from Big Bang nucleosynthesis so well is a powerful, albeit indirect, confirmation that this sea of neutrinos exists and has been with us since the very beginning. It's a triumphant success for the standard model of cosmology, but it also hints at potential surprises. Any discrepancy between the predicted and observed light element abundances could point to the existence of additional, unknown types of sterile neutrinos or other exotic particles that were also present in the early universe, contributing to the energy density and altering the nuclear recipe. The cosmic neutrino background also leaves its subtle mark on the more famous cosmic microwave background. While the CMB was released hundreds of thousands of years after the neutrinos decoupled, the two are deeply connected. The gravitational influence of the vast sea of relic neutrinos subtly affected the way sound waves traveled through the primordial plasma, leaving a specific imprint on the statistical properties of the hot and cold spots we see in the CMB today. Precision data from missions like the Planck satellite have allowed cosmologists to detect this imprint. They can't see the neutrinos directly, but they can see the gravitational shadows they cast on the CMB. This provides another independent and highly precise measurement that confirms the existence of the cosmic neutrino background and constrains the total mass of neutrinos. It's a remarkable convergence of evidence: galaxy clustering, a Big Bang nucleosynthesis, and the CMB all point to the same conclusion, painting a consistent picture of a universe permeated by these ghostly relics. Furthermore, this connection opens a fascinating, though speculative, link to dark matter. If dark matter particles interact with each other or with neutrinos, even very weakly, it would alter the way both components clump and stream through the cosmos. The precise properties of the cosmic neutrino background, once measured, could therefore serve as a new tool for probing the mysterious nature of dark matter itself, potentially revealing forces and interactions that are completely invisible to our current experiments. So we are left to ponder the profound secrets carried by these ancient, ghostly particles. What can the direct detection of a single relic neutrino, a particle that has been traveling undisturbed since the first second of time, possibly tell us? It would provide a direct measurement of the neutrino's mass, a fundamental parameter that remains one of the biggest unknowns in the standard model of particle physics. It could reveal if neutrinos are their own antiparticles, a property that could explain the matter-antimatter asymmetry of the universe, and it could uncover whether there are more than 3 types of neutrinos, opening a portal to physics beyond our current understanding. This line of inquiry naturally pulls our gaze toward the most speculative and exciting possibilities. Could the strange properties of neutrinos, particularly their quantum ability to oscillate between different types as they travel, be influenced by the hidden geography of reality? In theories with extraspatial dimensions, the way neutrinos oscillate could be subtly altered as their quantum waves propagate through the compactified, curled-up dimensions that may be woven into the fabric of spacetime. A precise study of the cosmic neutrino background, a fossil from a time when the universe was far hotter and denser, might reveal tiny anomalies in its expected properties, anomalies that point directly to the existence of these hidden realms. The ultimate detection of this primordial sea would therefore be more than just confirming a prediction. It would be opening a new sensory organ for the universe, allowing us to hear its first whisper, and in doing so, perhaps overhear the echoes of dimensions we have only ever dreamed of. Now let's zoom in on a cosmic puzzle that is deceptively small, a tiny anomaly in the chemical recipe of the universe that has stubbornly refused to be solved. In the first few minutes after the Big Bang, the cosmos was a seething nuclear furnace, fusing the primordial soup of protons and neutrons into the first light elements, vast amounts of helium, a little bit of deuterium, and trace quantities of a specific isotope known as lithium-7. Our theoretical models of this process, known as Big Bang nucleosynthesis, are spectacularly successful for helium and deuterium. Their predicted abundances match what we observe in the oldest corners of the universe with breathtaking precision. But for lithium, the calculations are off. The models tell us there should be about 3 times more lithium-7 out there than what we actually find when we look at the atmospheres of ancient stars in the halo of our galaxy. This is the lithium problem, a small but persistent chemical discrepancy that acts like a single wrong note in an otherwise perfectly performed cosmic symphony, suggesting that our understanding of the universe's very first minutes might be missing a crucial ingredient. Astrophysicist Brian Fields perfectly captured the nature of this enigma when he noted that the lithium discrepancy is a small but persistent thorn, indicating that our model of the first few minutes isn't perfect. This isn't a catastrophic failure of the Big Bang theory, but a precise and nagging clue. It tells us that while the broad strokes of our cosmic origin story are correct, there are subtle details in the nuclear physics of the infant universe that we have yet to fully grasp. The lithium problem forces us to ask whether we've missed a key nuclear reaction in our charts, whether unknown particles were interfering with the process, or if the conditions in that primordial forge were slightly different than we've assumed. It's a forensic investigation into a 3-minute-old crime scene, and the only evidence is the ancient chemical composition of the oldest stars we can find. To understand the depth of this puzzle, we need to look at the witnesses, ancient metal-poor stars. In astronomy, metals refer to any element heavier than helium. The first stars to form after the Big Bang were composed almost entirely of hydrogen and helium, with only the barest trace of lithium forged in the initial fireball. By studying the atmospheres of these incredibly old stars, which are found in the galactic halo and in globular clusters, astronomers can effectively take a core sample of the early universe's chemistry. These stars act as cosmic time capsules, preserving the primordial lithium abundance in their outer layers, and consistently, across many different observations, the measured amount of lithium-7 in these stars is only about 1/3 of the value predicted by our most sophisticated models of Big Bang nucleosynthesis. The data is robust and the discrepancy is clear, which means the solution must lie in revising our understanding of the physics that governed the universe during its first 3 minutes. So, where could the missing lithium have gone? Scientists have explored a fascinating array of possible fixes. One line of investigation focuses on the nuclear reaction rates themselves. The complex network of reactions that builds lithium-7 involves steps like the formation of beryllium-7, which later captures an electron to become lithium-7. If the rates of these reactions have small, unaccounted-for uncertainties, it could tip the balance and produce less lithium. However, laboratory experiments have constrained these rates quite well, and it seems unlikely that errors here are the sole culprit. Another compelling possibility is that lithium is being destroyed after its creation. Perhaps these ancient stars are not perfect time capsules after all. Processes in their interiors, like slow mixing or diffusion, could have dragged surface lithium down into hotter layers where it would be fused into heavier elements, gradually depleting the amount we see today. While this is a plausible mechanism for some stars, it's difficult to reconcile with the fact that the lithium abundance seems to be so uniform across a wide range of these ancient stars, which would have different internal structures and histories. The plot thickens when we connect this puzzle to other pillars of cosmology. The outcome of Big Bang nucleosynthesis is exquisitely sensitive to the density of ordinary matter, or baryons, in the early universe. We now have an incredibly precise measurement of this baryon density from the cosmic microwave background, courtesy of the Planck satellite. When we plug this independently measured value into the nucleosynthesis equations, the predictions for deuterium and helium match perfectly, but the lithium prediction becomes even more stubbornly high. This convergence is a double-edged sword. It confirms the overall consistency of our standard cosmological model, but it also isolates the lithium problem, telling us that the solution isn't a simple tweak to the overall matter density. It must be something more specific to the nuclear physics of lithium itself. This has led theorists to propose more exotic solutions that venture into new physics. One intriguing idea involves the ghostly neutrino. We know that neutrinos oscillate, changing from one type to another as they travel. If neutrinos in the early universe had different oscillation properties than they do today, perhaps due to interactions with a dense, primordial neutrino background or with other hypothetical particles, it could have altered the neutron-to-proton ratio at a critical moment. Since lithium production depends sensitively on this ratio, even a tiny shift could resolve the discrepancy. Another, even more speculative, idea points to dark matter. What if certain types of dark matter particles were unstable and decayed in the early universe? The energetic products of that decay could have bombarded the nascent nuclei, destroying the fragile beryllium-7 before it could decay into lithium-7, effectively snipping that branch off the nuclear reaction tree. This would be a stunning connection, linking the microscopic nature of dark matter to the macroscopic chemical composition of the cosmos. This elemental mystery, focused on a single isotope, ultimately forces us to confront a profound question about the dawn of time. Why did the universe, in its incredible creative fury, produce so little of this specific element, an element that sits in a crucial position on the periodic table? The answer may require us to look beyond the three-dimensional stage on which we perceive these nuclear reactions. Could the primordial processes that forged the elements have been subtly influenced by the presence of extra, compactified dimensions? In the incredibly high-energy, high-density environment of the first few minutes, the effects of hidden dimensions on fundamental forces and particle interactions might have been magnified. Perhaps the strength of the nuclear force was ever so slightly different, or the decay rates of key unstable isotopes were altered, all because the underlying fabric of reality had more hidden threads than we currently account for in our models. The lithium problem, therefore, is more than a chemical accounting error. It is a potential portal, a hint that the very first nuclear reactions were shaped by a physics that operates in more than the three spatial dimensions we call home. Now, let's turn our attention to a powerful cosmic phenomenon that acts as nature's own telescope, allowing us to literally see the invisible. Gravitational lensing occurs when the fabric of space-time is warped by a massive object, bending the path of light from a more distant source, much like a glass lens bends light. This effect, predicted by Einstein, typically creates beautiful, stretched arcs and multiple images of background galaxies. In most cases, the amount of lensing we observe is far stronger than what we would expect from the visible matter alone, the stars and the glowing gas. This is one of the most compelling pieces of evidence for the existence of dark matter halos, the vast, invisible spheres of matter that envelop galaxies and clusters, providing the extra gravitational muscle to bend the light. But sometimes the cosmic lens reveals something even stranger, a twist in the plot that challenges our simplest assumptions about this mysterious substance. The most famous and dramatic example of this is the bullet cluster. This isn't a single object, but the aftermath of a high-speed collision between two enormous galaxy clusters. When they smashed together, the different components of the clusters behaved in startlingly different ways. The clouds of hot, X-ray emitting gas, which make up the majority of the normal matter, collided and slowed down, creating a drag, much like two clouds of smoke would merge and billow. But when astronomers mapped the total mass using gravitational lensing, they found that the bulk of the mass, the dark matter, had sailed right through the collision completely unscathed. The dark matter and the visible gas were physically separated. This was a landmark observation, as astronomer Douglas Clow, who led this pivotal study, reflected. Lensing gives us a map of the invisible, but the details sometimes don't match our expectations. The bullet cluster was a triumph for the dark matter hypothesis because it showed that most of the matter is not only dark but also fundamentally different. It doesn't interact with itself or normal matter in any significant way apart from gravity. It seemed to be the ultimate proof that dark matter is a collisionless, ghostly substance. However, the universe, in its infinite complexity, soon provided a counterpoint. In another galaxy cluster, Abell 520, astronomers found a deeply puzzling configuration. Dubbed the train wreck cluster, Abell 520 showed a bizarre separation, but not the clean one seen in the bullet cluster. Here, the dark matter, as mapped by lensing, appeared to be concentrated in a central core that was largely devoid of the bright galaxies. The galaxies themselves seemed to have moved on, leaving their dark matter behind. This was the opposite of what simple theories predicted. If dark matter is just a passive gravitational scaffold, it should be closely associated with the galaxies, which are the most massive visible tracers. The Abel 520 anomaly suggests that in some environments, dark matter might be able to interact with itself through some unknown force, creating a kind of drag that causes it to lag behind the galaxies during a violent collision. This single observation fueled intense debates, forcing physicists to consider that dark matter might not be completely sterile. Perhaps it has a rich, hidden physics of its own, with particles that can occasionally collide or scatter off one another, a model known as self-interacting dark matter. These lensing anomalies have also breathed new life into a completely different school of thought, the idea that we don't need dark matter at all, but rather a modification to the laws of gravity itself. Theories like MUND, or modified Newtonian dynamics, propose that gravity behaves differently at the extremely low accelerations found in the outskirts of galaxies and in clusters. Proponents of MUND argue that these lensing patterns could be explained by a subtle change in how gravity works on cosmic scales, eliminating the need for an invisible substance. However, the bullet cluster presents a severe challenge for modified gravity. It's very difficult to explain how a modification of gravity could separate from the bulk of the normal matter, the hot gas without some form of unseen mass. The debate between dark matter and modified gravity is one of the most passionate in modern cosmology, and gravitational lensing provides the critical battleground where these ideas are tested. To understand how we gather this evidence, it's helpful to know the two primary flavors of gravitational lensing. Strong lensing produces those dramatic, unmistakable effects: giant arcs, rings, and multiple images of a single background galaxy. This happens when the alignment between the foreground mass, the lens, and the background source is almost perfect. It's a relatively rare and spectacular event. Weak lensing, on the other hand, is far more subtle but also more common. It doesn't create perfect rings or multiple images. Instead, it causes a coherent, slight stretching of the shapes of thousands of background galaxies, distorting them in a specific statistical pattern. By measuring the tiny, systematic alignments of these millions of faint, distant galaxies, astronomers can painstakingly reconstruct a detailed map of the intervening dark matter distribution, tracing out the vast, invisible cosmic web of filaments and voids. This technique is incredibly powerful, but it's also a monumental statistical and computational challenge, requiring some of the largest telescopes and most sophisticated algorithms in the world. This is where the next generation of observatories comes in. The European Space Agency's Euclid Space Telescope, launched in 2023, is a dedicated cosmology mission designed to tackle these very questions. Euclid will perform the most extensive weak lensing survey ever conceived, measuring the shapes of billions of galaxies across a third of the sky. Its exquisitely sharp and stable vision will allow it to create dark matter maps of unprecedented precision and scale. These maps will be crucial for distinguishing between different dark matter models. For instance, if dark matter is self-interacting, it will leave a specific signature in the shapes of dark matter halos, making them more spherical and smoothing out their central densities. Euclid's vast statistical power will be able to detect these subtle effects, potentially revealing the microphysical properties of dark matter particles from their macroscopic gravitational imprint on the cosmos. Similarly, these precise maps will put modified gravity theories to the test, checking whether the relationship between visible matter and gravitational pull holds firm across the entire history of the universe. The interpretation of all this data relies heavily on another crucial tool: supercomputer simulations. Cosmologists run immense numerical experiments, simulating the evolution of the universe from its initial conditions to the present day under different assumptions. They can create virtual universes with collisionless dark matter, with self-interacting dark matter, or even with modified gravity laws. They then observe these virtual universes, applying the same lensing techniques to their simulated galaxies. By comparing the lensing patterns from these different simulated universes to the real data from telescopes like Euclid, we can perform a cosmic matching game. Which simulated universe looks most like our own? The answer will tell us not just if dark matter exists, but what it's actually like. Do its halos have the fluffy cores predicted by self-interaction, or the sharp cusps of the simplest models? Do the filaments of the cosmic web appear as we expect, or are there twists and kinks that point to new physics? So, as we stand before these intricate maps of the unseen, we are forced to confront a question that gets to the very heart of our methods. Are these lensing anomalies, the strange separations and unexpected concentrations, simply flaws in our models, revealing a more complex astrophysics of galaxy formation that we haven't yet incorporated? Or could they be something far more profound? Could they be the first subtle hints that our understanding of gravity itself is incomplete in a way that goes beyond even modified Newtonian dynamics? This line of thinking naturally draws our curiosity toward the most speculative and exciting possibility. What if the way light bends around massive objects is influenced not just by mass in our three spatial dimensions, but by the geometry of hidden, extra dimensions? In certain string theory and brainworld scenarios, gravity is the only force that can propagate through the bulk of higher dimensional space. This could subtly alter how it warps space-time in our visible dimensions, potentially enhancing gravitational lensing effects in ways that mimic the presence of extra dark matter, or creating unique lensing signatures that wouldn't exist in a purely three-dimensional universe. The precise maps from Euclid might one day reveal such an anomaly, a pattern of light bending that can only be explained by gravity reaching out into the hidden architecture of reality. Imagine two magnificent kingdoms, each ruled by its own set of perfect, unshakable laws. In one kingdom, the realm of the cosmos, gravity weaves the fabric of space-time into the majestic curves that guide planets and galaxies, all described with breathtaking elegance by Einstein's general relativity. In the other kingdom, the quantum domain of the infinitesimally small, particles dance in a probabilistic haze governed by the equally powerful yet utterly different rules of quantum mechanics. For nearly a century, these two kingdoms have existed side by side, each supremely successful in its own domain. Yet where they meet, at the heart of a black hole or at the very moment of the Big Bang, their laws clash in a violent, nonsensical conflict. The grand challenge of uniting them into a single, coherent theory of quantum gravity stands as perhaps the most ambitious and profound quest in all of modern physics. It is a pursuit that aims to answer the ultimate question: what is the true, fundamental nature of the stage upon which the cosmic drama unfolds? As the renowned physicist Carlo Rovelli so aptly emphasizes, quantum gravity isn't just about black holes, it's about understanding the fabric of space-time itself. This isn't just a technical puzzle for theorists, it is a journey to the bedrock of reality, seeking the language that can describe both the dance of the stars and the flutter of a quantum particle. The stakes of this quest could not be higher, for without a theory of quantum gravity, our understanding of the universe is fundamentally incomplete at its most extreme boundaries. Consider the very beginning of everything, the Big Bang singularity. General relativity predicts a point of infinite density and temperature where its own equations break down completely. It is a place where the very concepts of space and time cease to have meaning, a cosmic before that physics cannot currently describe. Similarly, deep inside a black hole, matter is crushed into another singularity, a one-way door to a realm our laws cannot penetrate. This conflict isn't just philosophical, it has tangible consequences like the black hole information paradox we explored earlier. If information truly vanishes into a singularity, it violates the core tenets of quantum mechanics. A successful theory of quantum gravity would replace these nonsensical infinities with a coherent physical description, telling us what truly happens at the center of a black hole and what, if anything, came before the Big Bang. It would be the final piece in our fundamental understanding of the forces of nature, a theory of everything that can describe the universe from its first moment to its last. To tackle this monumental problem, physicists have developed several brilliant yet wildly different candidate theories. One of the most prominent is string theory. This framework proposes that the fundamental constituents of reality are not point-like particles, but incredibly tiny, vibrating loops of energy strings. Just as different vibrations of a violin string produce different musical notes, the various ways these fundamental strings vibrate manifest as the different particles we observe: electrons, quarks, photons, and even the hypothetical graviton, the quantum carrier of gravity. The profound elegance of string theory is that it naturally includes gravity within its quantum mechanical description. However, this elegance comes at a cost. The mathematics of string theory only works consistently in a universe with more than the three spatial dimensions we experience. It requires extra, compactified dimensions curled up into shapes so small we cannot perceive them, providing the necessary room for the strings to vibrate in just the right ways to produce the rich tapestry of our physical world. In this view, gravity may appear weak because it is diluted, spreading out into these hidden dimensions. A radically different approach is known as loop quantum gravity. Instead of replacing particles with strings, this theory takes Einstein's vision of spacetime as a dynamic entity even more seriously. It proposes that space itself is not a smooth, continuous backdrop, but is woven from a fabric of finite, discrete loops. Picture the fabric of reality as a mesh, a network of a billion tiny, interconnected threads. Space is quantized, meaning it comes in tiny, indivisible units, a smallest possible volume. This granular structure becomes apparent only at the incredibly tiny Planck scale, far beyond our current means of direct observation. In loop quantum gravity, there are no singularities. Instead, the intense gravity at the center of a black hole or the beginning of the Big Bang leads to a quantum bounce, a repulsive force that prevents collapse into infinity. It is a compellingly direct solution that quantizes space and time themselves, offering a universe that is fundamentally pixelated. A third, less mainstream but intriguing approach is the idea of asymptotic safety in quantum field theory. This proposal suggests that perhaps we don't need exotic strings or loops at all. Maybe gravity can be successfully described within the framework of quantum field theory, the very language of the Standard Model, if the theory possesses a special property known as asymptotic safety. This would mean that at extremely high energies like those of the Big Bang, the strength of gravity's interaction reaches a fixed, safe value rather than blowing up to infinity. It's a minimalist approach that tries to tame gravity's quantum wildness without adding extra dimensions or fundamentally changing the nature of spacetime, though proving this property definitively remains a formidable mathematical challenge. These theoretical battles are fought over profound conceptual issues such as the problem of time. In general relativity, time is dynamic, a flexible dimension that is woven into the fabric of spacetime and is affected by matter and energy. In the standard formulation of quantum mechanics, time is an external, absolute parameter, an unchanging stage on which the quantum events unfold. Reconciling these two views is a deep philosophical and technical hurdle. Then there is the holographic principle, which suggests that all the information describing a volume of space can be thought of as encoded on its boundary, like a three-dimensional image projected from a two-dimensional surface. This radical idea, born from the study of black hole thermodynamics, implies that our perception of a three-dimensional world may be a kind of magnificent illusion, a hologram, and that a theory of quantum gravity must ultimately be a theory that describes physics on a lower dimensional surface. But how can we possibly test these mind-bending ideas when they deal with energies and scales far beyond our reach? The ingenuity of physicists has opened a few promising windows. The detection of gravitational waves has provided a new way to probe the fabric of spacetime. While current observations from LIGO and Virgo beautifully confirm general relativity, future observatories, like the space-based LISA antenna, could potentially detect subtle imprints of quantum gravity. For instance, if spacetime has a granular structure as loop quantum gravity suggests, it might leave a faint, characteristic noise in the gravitational wave signal, a subtle graininess in the ripples themselves. Another avenue involves studying the light from the most violent explosions in the universe, gamma-ray bursts. Photons of different energies from these bursts travel across billions of light-years to reach us. If spacetime is indeed discrete at the Planck scale, the highest energy photons might travel very slightly slower than their lower energy counterparts, as they would effectively bump against the fine grain of spacetime. While no such effect has been conclusively observed, even setting limits with these cosmic messengers helps to constrain the wild landscape of possible theories. On Earth, incredibly sensitive experiments using atom interferometry are searching for minuscule deviations in how gravity behaves at microscopic distances, a regime where quantum gravitational effects might finally become noticeable. So we are left to ponder a question that strikes at the very methodology of science. How can two of our most successful, well-tested theories in all of physics be fundamentally and stubbornly incompatible when pushed to their limits? It is a humbling reminder that our understanding of the cosmos, for all its sophistication, is still a work in profound progress. The resolution will undoubtedly require a perspective shift as dramatic as the one from Newtonian mechanics to relativity. And in this search, the recurring theme of hidden dimensions offers a particularly compelling pathway. Could it be that the elusive glue that binds the cosmic and the quantum is not found in our three-dimensional realm at all? String theory's explicit reliance on extra dimensions is the most direct version of this idea, but even other approaches hint that the true, fundamental degrees of freedom of nature might reside in a higher dimensional reality, with our familiar world being a beautiful and complex projection. The quest for quantum gravity, therefore, is more than a unification of forces. It is the ultimate exploration of the universe's hidden architecture, an effort to read the full, multidimensional blueprint of reality. This monumental endeavor to find a single, unified language for physics doesn't exist in a vacuum. Its success would ripple across all of cosmology, providing the essential tools to finally solve the cosmic riddles of the Big Bang, black holes, and the very origin of spacetime. But what if our universe, with its finely tuned constants and unique history, isn't the only one? What if it's just a single page in an infinite cosmic library, one volume among countless others on a shelf that stretches beyond imagination. This is the staggering premise of the multiverse, a concept that suggests our entire observable cosmos is just one of a vast, perhaps infinite, ensemble of universes, each with its own distinct set of physical laws, constants, and potentially even different numbers of spatial dimensions. This idea doesn't spring from science fiction, but from the cutting edge of cosmological theory, emerging naturally from concepts like eternal inflation and the intricate mathematics of string theory. It's a vision that offers a breathtakingly elegant solution to the puzzle of fine-tuning, suggesting that the seemingly miraculous settings on our cosmic control panel aren't a miracle at all, but a simple consequence of probability. If every possible setting is tried somewhere, then it's no surprise that we find ourselves in one of the rare universes where life can exist. As the pioneering cosmologist Alan Guth, father of the inflationary theory, has reflected, the multiverse could be the ultimate Copernican revolution, showing we're not special, just lucky. We were dethroned from the center of the solar system, then from the center of our galaxy. The multiverse suggests we are not even at the center of reality itself, but merely residents of one utterly typical cosmic neighborhood in a metropolis of universes. To make sense of this vast and often confusing concept, physicist Max Tegmark has provided a useful framework, categorizing the multiverse into 4 distinct levels, each more radical and mind-expanding than the last. Level 1 is perhaps the easiest to grasp. It simply posits that if the universe is truly infinite in extent, then every possible configuration of matter must repeat somewhere. Far beyond our cosmic horizon, there is another identical Milky Way galaxy with an identical Earth and an identical you, reading an identical sentence. In this view, the multiverse isn't about different laws, but about the sheer statistical inevitability of repetition in an infinite space. Level 2 takes us a step further into the realm of inflationary bubbles. This is the direct consequence of eternal inflation, where the rapid expansion of spacetime never truly stops globally, but instead, pockets of space randomly stop inflating, each one bubbling off to become its own separate, self-contained universe. Crucially, in this scenario, each of these bubble universes could have experienced a different kind of symmetry breaking as it cooled, leading to fundamentally different physical laws and constants. In one bubble, the weak nuclear force might be stronger. In another, electrons might be heavier. Our entire cosmos is just one of these bubbles, its properties set by the random lottery of its formation. The third level emerges from the strange world of quantum mechanics, specifically the many worlds interpretation. In this view, every time a quantum event has multiple possible outcomes, the universe doesn't choose one. Instead, it splits, dividing into multiple, equally real branches. Did that radioactive atom decay or not? The universe splits, creating one timeline where it did and another where it did not. Over the history of the cosmos, this process has generated an unimaginably vast tree of parallel realities, all existing simultaneously but forever disconnected from one another. Here, the other universes aren't far away in space, but are layered right on top of us, separated not by distance but by the branching of quantum probability. Finally, level 4 is the most abstract and all-encompassing of all, the mathematical multiverse. This idea suggests that every mathematically consistent structure actually exists as a physical reality. If a set of laws and initial conditions can be described by mathematics, then a universe governed by those laws is out there, somewhere in the multiverse. In this ultimate vision, our universe isn't just one of many with slightly different constants. It is one of an infinite variety, including some with entirely different dimensionalities, fundamental forces, and forms of existence we cannot even begin to conceive. The primary scientific motivation for taking these dizzying ideas seriously is their power to solve the fine-tuning problem through the anthropic principle. If there is only one universe, the precise calibration of its constants for life seems to demand an explanation, either a cosmic designer or an incredibly unlikely fluke. But in a multiverse, especially the level 2 inflationary kind, the problem simply evaporates. Of course, we find ourselves in a universe capable of supporting conscious life. We could not possibly observe one that wasn't. We are simply the winners of a cosmic lottery, living in one of the rare, bio-friendly bubbles in a frothing meta-universe filled mostly with barren, lifeless voids. This is not a proof of the multiverse, but it is a compelling argument for its plausibility. Beyond this philosophical reasoning, scientists are actively searching for more tangible, physical evidence. One promising avenue is to look for the scars of ancient cosmic collisions. If our universe is one bubble in a greater multiverse, it's possible that during the violent period of inflation, our bubble collided with a neighboring one. Such a colossal impact would have sent ripples through the fabric of our newborn cosmos, potentially leaving a distinct, asymmetric imprint on the cosmic microwave background, a cold spot or a specific pattern of polarization that cannot be explained by standard physics. While tentative claims have been made, such as the famous cold spot we discussed earlier, no definitive evidence of a bubble collision has yet been confirmed, but the search continues in the precise data from satellites like Planck. The greatest challenge facing the multiverse concept, however, is the charge of unfalsifiability. If these other universes are permanently beyond our observational reach, separated by unimaginable distances or existing in separate quantum branches, can the multiverse truly be considered a scientific theory? Critics argue that it risks becoming a metaphysical speculation, an untestable idea that explains everything and therefore nothing. Proponents counter that the concept is grounded in well-established physics like inflation and quantum mechanics, and that indirect evidence, like the confirmation of a specific signature in the CMB or a deeper understanding of the string theory landscape, could provide compelling, if not direct, support. The debate is a healthy one, forcing scientists to confront the very definition of science and the limits of what we can ever hope to know. It pushes us to develop new kinds of tests and to think more creatively about what constitutes evidence for a reality that may be fundamentally unobservable in its entirety. This entire breathtaking edifice of parallel worlds and bubble universes finds a natural and perhaps necessary home in the concept of hidden dimensions. String theory, one of the leading candidates for a theory of everything, doesn't just allow for a multiverse, it practically demands one. The theory suggests the existence of a vast landscape of possible stable configurations for its extra, compactified dimensions, a number estimated to be an almost incomprehensible 10 to the power of 500. Each of these configurations corresponds to a universe with a different vacuum energy and different effective laws of physics. Our universe, with its specific value for the cosmological constant and its 4 fundamental forces, is just one point in this colossal landscape. The diversity of the multiverse, therefore, could be directly enabled by the rich and varied geometry of these hidden spatial dimensions. The different settings for the laws of physics in different bubbles or branches might ultimately be traced back to the different ways in which the extra dimensions are curled up and stabilized. In this view, the multiverse is not a chaotic jumble, but a structured, if unimaginably vast, landscape of possibilities, with the hidden dimensions acting as the fundamental substrate from which all cosmic diversity springs. This leads us to a final, profound contemplation on the nature of reality itself. Is the multiverse a legitimate scientific theory, a necessary consequence of our best physical models, or is it a step too far into the realm of philosophical speculation that can never be tested? The answer will determine whether we ultimately accept a single, special universe, finely tuned for our existence, or embrace a cosmic democracy of infinite worlds, where our reality is just one thread in an infinitely rich and varied tapestry, woven from the hidden dimensions of a grander meta-reality. Deep within the heart of a black hole, where gravity has won its ultimate victory, our current understanding of physics reaches a terrifying and illogical conclusion. According to Albert Einstein's theory of general relativity, all the matter that has ever fallen into the black hole, entire stars, vast clouds of gas, and perhaps even unlucky spacecraft, is crushed into a single point of zero volume and infinite density. This is the singularity, a place where the reliable fabric of spacetime itself is torn apart, where the equations that so beautifully describe the orbits of planets and the bending of light simply spit out nonsensical infinities. It is a glaring paradox. Our most successful theory of gravity predicts its own downfall, pointing to a realm where its own rules cease to apply. This cosmic dead end is the most powerful argument that we are missing a crucial piece of the puzzle, a theory that can marry the vast cosmic scales of gravity with the bizarre quantum rules that govern the subatomic world. The singularity is the universe's way of screaming that we need quantum gravity to understand the final fate of matter. What saves this mathematical catastrophe from being a direct affront to our reality is the black hole's event horizon. This is the point of no return, the invisible boundary that shuts the singularity off from the rest of the universe. Whatever horrors or wonders lie at the center are forever hidden behind this one-way curtain. This profound idea was central to the work of Stephen Hawking, who, along with physicist Roger Penrose, developed the singularity theorems that proved such points are an inevitable outcome of general relativity under certain conditions. Hawking famously quipped that the universe doesn't allow naked singularities, it dresses them in event horizons. This cosmic censorship hypothesis is a fascinating conjecture that suggests the laws of physics abhor a naked singularity, one that is not hidden behind an event horizon because its presence would shatter our ability to predict the future. Cause and effect would break down entirely at such a point, creating unpredictable chaos in the cosmos. The fact that we have never observed such a thing suggests that nature has a built-in modesty, a preference for keeping its most profound secrets veiled from view. Faced with the problem of the infinite singularity, theoretical physicists have not been idle. They have crafted several brilliant, though still speculative, alternatives that aim to replace this mathematical monstrosity with something more physically sensible. One compelling idea comes from loop quantum gravity, a theory that proposes spacetime is not smooth and continuous, but is instead woven from a fabric of tiny, discrete, indivisible loops. In this granular view of reality, the immense gravitational pull at the center of a black hole does not lead to an infinite crush. Instead, it triggers a tremendous repulsive force, a quantum bounce. Imagine the collapse of a dying star reaching a point of such incredible density that the quantum nature of spacetime itself pushes back, like a cosmic spring compressed to its limit. The matter wouldn't vanish into a singularity, it would rebound, potentially exploding outward into a new region of spacetime. In this scenario, a black hole could be a gateway, a tunnel, a wormhole connecting our universe to another, or perhaps even giving birth to a new baby universe of its own, with the Big Bang on the other side being the aftermath of a quantum bounce in a pre-existing cosmos. String theory, another leading candidate for quantum gravity, offers its own set of exotic solutions, One particularly intriguing idea is the fuzzball proposal. In this picture, the black hole is not a vacuum surrounding a central point of infinite density. Instead, the entire interior of the event horizon is filled with a giant, tangled ball of strings, the fundamental vibrating loops that the theory proposes as the building blocks of reality. This fuzzball has a complex dynamic structure that extends all the way to the horizon, eliminating the singularity entirely. The infinite density is smoothed out into a vast, albeit still incredibly dense, quantum object. Another radical string-inspired idea is the firewall hypothesis. This suggests that the event horizon itself might not be the smooth, uneventful space that relativity predicts. Instead, it could be a blazing wall of high-energy particles that would instantly incinerate anything attempting to cross it. While this idea solves certain paradoxes related to information, it violently contradicts the cornerstone principle of general relativity that an astronaut falling into a black hole should notice nothing special as they cross the horizon. The debate between these models highlights the creative turmoil in theoretical physics as it grapples with the black hole's deepest secret. The resolution of the singularity problem also has dramatic implications for one of science fiction's most beloved concepts, time travel. The theoretical underpinnings for a time machine often involve creating a closed time-like curve, a path through space-time that loops back onto itself, allowing you to travel into your own past. General relativity shows that the extreme warping of space-time near a singularity could, in principle, create such paths. If a naked singularity, one without an event horizon, could exist, it might allow for the construction of a time machine. However, most physicists, guided by the cosmic censorship hypothesis, believe this is impossible. The universe seems to have a built-in protection against such paradoxes. If the singularity is replaced by something else, like a fuzzball or a quantum bounce, the conditions that could permit time travel might be eliminated altogether. The true nature of the black hole's core, therefore, doesn't just tell us about the fate of matter. It may also enforce the fundamental arrow of time, ensuring that cause always precedes effect and that history remains a fixed, unchangeable record. So we are left staring into the abyss, forced to ask a question that pushes at the very limits of human comprehension. What truly lies at the heart of a black hole? Is it a gateway to another universe, a blazing firewall, a tangled quantum fuzzball, or a point of impossible infinity? The answer will rewrite our understanding of reality itself. And this profound curiosity inevitably draws our imagination toward the architecture of space. Could the key to smoothing out this terrifying infinity lie not in our three familiar dimensions, but in realms we cannot see? In the complex geometries of string theory, the extra, compactified dimensions could provide the necessary room for the fundamental strings to vibrate in such a way that the infinite density of a singularity is naturally resolved. The crushing gravity of the black hole from our three-dimensional perspective might be the gentle folding of space-time in a higher dimensional landscape. The singularity, therefore, might not be a flaw in Einstein's universe, but a signpost pointing directly toward the hidden, multidimensional foundations of all things, suggesting that the ultimate nature of gravity's extremes can only be understood by peering into the full, rich tapestry of a cosmos with more dimensions than we can perceive. When you look at a map of the cosmic microwave background, the universe's first light, you expect to see a canvas of random, gentle variations, a testament to the primordial quantum jitters that seeded all of cosmic structure. But then your eye is drawn to one particular feature, a vast and chillingly cold patch in the southern sky, so large and so unusually frigid that it stands out like a cosmic sore thumb. This is the cold spot, an anomaly spanning over 1 billion light-years, first identified with startling clarity by NASA's Wilkinson microwave anisotropy probe, and later confirmed by the even more precise Planck satellite. Its temperature is a mere 70 microkelvins colder than the average CMB, a tiny number that belies its profound implications. This isn't just a random statistical fluctuation. It is a feature so rare and so extreme that it challenges the very foundations of our standard inflationary cosmology, forcing us to consider whether it is a bizarre fluke of nature, a shadow cast by a colossal emptiness, or something far more spectacular, a bruise left by a collision with another universe. The most conventional explanation, and the one that scientists have pursued with vigor, is that the cold spot is not a feature of the primordial CMB at all, but rather an effect created by a vast supervoid, an enormous region of space with a significantly lower density of galaxies than the cosmic average sitting between us and the ancient light. According to general relativity, as light travels through the universe, its energy is affected by the gravitational potential of the structures it passes. When a CMB photon enters a large underdense region like a supervoid, it loses energy climbing out of the gravitational well, a phenomenon known as the integrated Sachs-Wolf effect. This energy loss should manifest as a slight cooling in the CMB temperature in that direction. So, the search began to find the supervoid responsible for the cold spot. Astronomers have indeed found a large underdensity of galaxies, known as the Eridanus supervoid, roughly aligned in that part of the sky. However, there's a significant problem. The size and depth of this observed void don't seem nearly sufficient to account for the dramatic coldness and immense scale of the CMB anomaly. The cooling it should produce through the ISW effect is far weaker than what we actually observe. This mismatch has led to a stalemate, leaving the void explanation as a possible but unsatisfying partial answer, a suspect that was at the scene of the crime but may not have had the strength to commit the act. This failure of the simple void model has opened the door to truly mind-bending alternatives, the most dramatic of which comes from theoretical physicist Laura Mersini-Houghton. She proposes that the cold spot is not an imperfection in our universe, but a scar from its violent birth in a wider multiverse. Her theory suggests that in the very first moments of cosmic inflation, our budding universe was gravitationally entangled with a neighboring one. As the two bubbles of spacetime rapidly expanded, they briefly brushed against each other. This cosmic collision would have drained energy from the contact region in our universe, leaving behind a permanent, cold imprint on the CMB, a cosmic fingerprint from a reality we can never directly visit. As Mersini-Houghton poetically describes it, the cold spot might be a bruise from a cosmic encounter we can't see. This idea pushes the boundaries of cosmology into the realm of the multiverse, suggesting that the largest structure we can map on the sky might be direct evidence for a reality beyond our own. To test these competing ideas, scientists have turned to a powerful tool, gravitational lensing. If the cold spot is caused by a vast supervoid, its gravitational field should subtly distort the light from galaxies behind it, creating a specific, measurable lensing signature. However, detailed analyses of the lensing data in the cold spot region have yielded confusing results. Some studies find less lensing than would be expected for a void massive enough to cause the observed cooling, further weakening the supervoid hypothesis. Other investigations have meticulously mapped the distribution of galaxies in that direction, finding that while there is an underdensity, it is not a single, simple void but a more complex and extended structure, perhaps a chain of connected smaller voids. The Planck satellite's final data release confirmed the cold spot's existence beyond doubt, but ultimately left its origin as an open question. its precise statistical significance hovering on the edge of what could be a mere chance occurrence, keeping the mystery tantalizingly alive. The statistical rarity of the cold spot is itself a central part of the puzzle. In a universe governed by the standard inflationary model and Gaussian random fluctuations, a feature this large and this cold is incredibly unlikely. Some calculations suggest the probability of such a spot appearing by pure chance is less than 2%. This low probability is what fuels the search for exotic explanations. Is it a 1 in 50 cosmic coincidence, a statistical outlier that our universe just happens to possess? Or is its very improbability the key clue, a signal that our standard model is missing a crucial ingredient, something that can naturally produce such rare, large-scale anomalies? This question forces cosmologists to walk a fine line between dismissing a genuine mystery as a fluke and prematurely embracing speculative physics. This entire investigation into the cold spot's origin naturally pulls our gaze toward the fundamental architecture of reality. Could the strange properties of this anomaly be explained not by a collision with another universe, but by the hidden geometry of our own? In theories involving extraspatial dimensions, the fabric of our cosmos is embedded within a higher dimensional bulk. The process of inflation and the subsequent evolution of the universe could have been influenced by the specific way these extra dimensions are compactified and stabilized. It is conceivable that a particular configuration of these hidden dimensions created a persistent, large-scale inhomogeneity in the gravitational potential of our three-dimensional space, a kind of cosmic wrinkle. This wrinkle would then imprint itself on the CMB, creating a feature like the cold spot without the need for a multiverse collision or an insufficient supervoid. The cold spot, in this view, would be a shadow, a projection from the higher dimensional geometry onto our observable sky, a permanent reminder that the true stage of the cosmos has more dimensions than we can directly perceive. The enduring mystery of this frigid patch on the infant universe's face challenges us to decide whether we are looking at a random quirk of chance, the fingerprint of a sibling cosmos, or the subtle signature of the hidden dimensions that shape everything. And so we arrive at a cosmic riddle that is, in many ways, the most intimate and profound of all, for it turns the telescope of inquiry inward toward the very instrument doing the observing. We have journeyed through the vastness of space and the weirdness of the quantum realm, but now we must confront the nature of the consciousness that makes this journey possible. Here is the philosophical twist that ties the cosmos to the mind. Could consciousness itself be not just a passive product of the universe, but an active player in its very unfolding? This idea finds a startling foothold in one of the most baffling aspects of quantum mechanics, the observer effect. In the famous double-slit experiment, particles like electrons seem to behave as spread-out waves when no one is looking. But the moment a measurement is taken to determine which path they take, they snap into definite particle-like locations. It's as if the very act of observation collapses a haze of possibilities into a single, concrete reality. This has led some of the greatest minds in physics to wonder if consciousness is the crucial ingredient that completes the universe, transforming potential into the actual world we experience. The legendary physicist John Wheeler took this idea to its most radical conclusion with his concept of the participatory universe. He envisioned a cosmos that only comes into full being through the act of observation by conscious beings. In his view, we are not merely bystanders on a pre-existing cosmic stage, but essential actors in an ongoing drama of creation. As he so eloquently put it, we are not just bystanders but actors in the cosmic drama. He imagined a universe that, in its earliest moments, was a nebulous cloud of unrealized potential, a vast set of quantum possibilities. It was only much later, with the emergence of the first conscious observers, whether humans on Earth or other beings elsewhere, looking back at the light from the Big Bang and measuring the properties of atoms, that the universe's past was retroactively solidified. In this breathtaking vision, our present-day observations help to fix the history of the cosmos, making us partners in a grand, time-spanning loop of self-creation. This perspective profoundly reshapes the anthropic principle, the idea that the universe's constants are fine-tuned for life. It suggests that the universe is not just coincidentally suitable for observers, but that observers are necessary to bring the universe into its finished state, weaving together the cosmic and the conscious in an inseparable bond. This line of thinking places us squarely in the middle of a fierce and ancient debate about the fundamental nature of consciousness. On one side stands the dominant view in neuroscience, materialism. This position holds that consciousness is an emergent property, a sophisticated software program that runs on the wetware of the brain. Just as the phenomenon of wetness emerges from the collective behavior of countless water molecules, but is not a property of any single molecule, consciousness emerges from the incredibly complex network of neurons firing in our skulls. From this perspective, when the brain dies, consciousness ceases, much like a flame being extinguished. It is a beautiful and intricate illusion generated by purely physical processes, with no need for any mystical or fundamental ingredients. The task of science, then, is to completely map how these neural circuits give rise to subjective experience, a challenge often called the easy problem of consciousness. But another school of thought, growing in prominence, argues that this materialist view misses the point entirely. This is panpsychism, the idea that consciousness is not an emergent latecomer to the universe, but a fundamental feature of it, as basic as space, time, and matter. Panpsychists propose that some form of primitive, subjective experience exists all the way down the chain of being. An electron may not be self-aware or have thoughts, but it might possess a faint glimmer of proto-consciousness, a single note of experience. In this view, the human mind is not a generator of consciousness, but rather a complex receiver or amplifier, an orchestra that consolidates these countless tiny notes into the rich symphony of our full awareness. The philosopher David Chalmers framed the core issue as the hard problem of consciousness. Why should all that neural processing, all those electrical and chemical signals, feel like anything from the inside? Why do we have the subjective, qualitative experience of the redness of red, the pain of a headache, or the awe of a starry night? Materialism can describe the correlates of these states in the brain, but it struggles to explain why they are accompanied by an inner life at all. Panpsychism offers a direct, if speculative, answer. They feel like something because feeling, in its most basic form, is already a property of the universe's building blocks. The quest to test these ideas has led to some of the most controversial experiments in modern science, venturing into the fuzzy borderland between quantum physics and biology. Some researchers, like Roger Penrose and Stuart Hameroff, have proposed that the seat of consciousness lies in the brain's microtubules, tiny protein structures within neurons. They suggest that these microtubules are capable of harnessing quantum effects, and that the collapse of the quantum wave function within them gives rise to moments of conscious experience. This or theory is highly debated and faces immense skepticism, as the warm, wet, and noisy environment of the brain seems hostile to the delicate state of quantum coherence, which usually requires extreme cold and isolation to be maintained. Yet, the very attempt to bridge the quantum and the cognitive highlights a deep intuition that the solution to the mystery of consciousness might be found not in classical biology alone, but in a deeper understanding of information and physics. This brings us to the concept of information integration as a potential measure of consciousness. Giulio Tononi's integrated information theory proposes that consciousness corresponds to a system's ability to integrate information in a way that the whole is more than the sum of its parts. The more interconnected and differentiated a network is, the higher its degree of consciousness, or phi. A photodiode has a very low phi. It can only register light or dark. The human brain, with its trillions of intricate connections, has a very high phi, resulting in our rich inner world. This theory provides a potential framework for detecting consciousness in non-biological systems. Could a sufficiently advanced artificial intelligence with a complex and integrated architecture become conscious, and what about cosmic structures? The universe itself is a vast, interconnected network of causally influencing parts. While its phi would be astronomically difficult to calculate, the idea raises a staggering question. Could the cosmos as a whole possess a form of consciousness, a slow, vast, and cosmic mind of which we are tiny, fleeting fragments? This speculation forces us to reconsider our search for extraterrestrial intelligence. If consciousness is truly fundamental, then it may not be limited to carbon-based, human-like life forms. We might be searching for biological aliens when we should be looking for signs of any complex, integrated system, perhaps one that is planetary or even stellar in scale. Furthermore, if our own consciousness can influence the outcome of quantum experiments, as some interpretations suggest, then could it, on some imperceptible level, be influencing the cosmological observations we make? Are we, in some small way, co-creating the universe we measure, from the quantum foam to the large-scale structure of galaxies? This idea, while far from the scientific mainstream, challenges the ideal of a perfectly objective science and places us back in the participatory role that Wheeler envisioned. So we are left with the most personal and profound of all the cosmic riddles. Is the universe, through us and perhaps other forms of awareness, becoming conscious of itself? Are we the means by which the cosmos witnesses its own beauty, contemplates its own origins, and unravels its own mysteries? And if consciousness is indeed a fundamental thread in the fabric of reality, could it be intertwined with the very hidden dimensions we have been exploring? In theories where our three-dimensional world is a projection from a deeper reality, might consciousness be the interface, the unique faculty that allows us to interact with, or even arise from, these hidden realms? The nature of consciousness remains the final, and perhaps most impenetrable, frontier, a mystery that sits at the intersection of the cosmos and the self, challenging us to understand not just the universe out there, but the one right here within. For years, the Fermi Gamma-ray Space Telescope has been silently mapping the high-energy sky, and in its data from the very heart of our Milky Way, it found something that shouldn't be there, a mysterious, diffuse glow of gamma rays emanating from the galactic center, an excess that stands out against the known astrophysical background. This isn't just a slight statistical bump. It's a significant overabundance of light at very specific energies, concentrated between 1 and 3 giga-electronvolts, a range that just so happens to be a sweet spot for certain theoretical models of dark matter. Picture our galaxy's core as a bustling, chaotic metropolis, a place teeming with stellar nurseries, spinning pulsars, and the supermassive black hole Sagittarius, a star. It's an incredibly challenging environment to interpret, filled with known sources of gamma rays. Yet, this particular signal has a smooth, widespread distribution that seems to blanket the central region, a characteristic that has led some scientists to wonder if we are finally seeing the indirect signature of dark matter particles annihilating each other. As astrophysicist Tracy Slatire aptly described the situation, the galactic center is a messy place, but this signal could be the smoke from dark matter's fire. It's a tantalizing possibility that after decades of searching, we might be seeing the faint, energetic aftermath of the universe's most elusive substance revealing itself. If this gamma-ray excess truly is the signature of dark matter, the leading candidate responsible is a class of particles known as weakly interacting massive particles, or WIMP. According to this elegant theoretical framework, when two WIMP collide, they can annihilate each other, transforming their mass directly into energy and producing a cascade of standard model particles, including the gamma-ray photons that Fermi detects. The specific energy range of the observed excess, that 1 to 3 giga-electronvolt peak, matches predictions for WIMP with a mass around 30 to 40 times that of a proton. Furthermore, the way this glow is distributed spatially across the galactic center is also telling. It aligns with what cosmologists would expect from the predicted density profile of the dark matter halo that envelops our galaxy. The halo should be most dense at the very center, and the gamma-ray signal appears to be as well, creating a compelling, though not definitive, correlation. The intensity of the signal also depends on the annihilation cross-section, a measure of how likely the WIMP are to collide and destroy each other. Intriguingly, the strength of the signal required to produce the observed gamma rays points to a cross-section that is remarkably consistent with the value needed for WIMP to naturally account for the correct abundance of dark matter in the universe through a process known as thermal freeze-out in the early cosmos. It's as if the universe left us a clue not just in the present, but also in the relic density from its infancy, and this signal seems to point to the same answer. However, the path to a dark matter discovery is never straightforward, and the galactic center is a notoriously complicated place. The primary alternative explanation is that this gamma-ray excess is not from dark matter at all, but is instead produced by a large population of unresolved astrophysical sources. The most prominent candidates are millisecond pulsars, ancient, rapidly spinning neutron stars that have been spun up by accreting material from a companion star. These objects are known to emit powerful beams of gamma radiation, and they are incredibly faint and difficult to detect individually at such a great distance. It is entirely plausible that the galactic center, a region of immense stellar density, hosts thousands of these faint pulsars. Together, their collective, unresolved glow could perfectly mimic the smooth, diffuse signal that we attribute to dark matter annihilation. Distinguishing between these two scenarios is one of the most active and contentious areas in high-energy astrophysics today. The key lies in the fine details. A dark matter signal should be perfectly smooth, while a population of pulsars would, with sufficiently sensitive observations, eventually resolve into individual points of light. Current analyzers walk a razor's edge, with some studies claiming the signal is too smooth to be explained by known pulsar populations, while others suggest there is just enough small-scale clumpiness to hint at a collection of discrete sources. To help break this deadlock, scientists use a powerful control group, dwarf spheroidal galaxies. These are small, faint satellite galaxies that orbit the Milky Way, and they are fascinating because they are believed to be massively dominated by dark matter. They have very few stars and a minuscule amount of normal matter, making them exceptionally clean laboratories. If the same WIMP annihilation process that is hypothesized for the galactic center is real, then these dwarf galaxies should also be producing a faint glow of gamma rays. The Fermi collaboration has performed a combined analysis of many of these dwarfs, effectively stacking their data to look for a collective signal. So far, no significant gamma ray emission has been detected from them. This null result is a serious constraint. It places upper limits on the annihilation cross-section of WIMP that are in some tension with the signal from the galactic center. If the galactic center excess is truly from dark matter, then why don't we see a corresponding signal from the dwarfs? Proponents of the dark matter interpretation argue that the dwarfs simply have much lower dark matter densities, making the signal exponentially fainter and potentially undetectable with current instruments, while the galactic center, with its incredible density, is uniquely bright. The debate continues, highlighting the critical need for more data and more powerful tools. The next great leap in this investigation will come from the Cherenkov Telescope Array, or CTA. This ambitious next-generation observatory, currently under construction, will not look at gamma rays directly from space, but will instead detect the fleeting flashes of blue Cherenkov light that these high-energy photons create when they strike the Earth's atmosphere. The CTA will have a much higher resolution and sensitivity than Fermi, particularly in the very energy range of the galactic center excess. It will be able to see the galactic center with a sharper eye, potentially resolving faint point sources that are currently blurred together into a smooth glow. If the excess remains stubbornly smooth and unresolved even under CTA's gaze, the case for dark matter will grow substantially stronger. Conversely, if CTA starts to pick apart the glow into thousands of individual pulsars, the dark matter interpretation would face a major setback. This future observatory represents our best hope for cutting through the astrophysical fog and determining the true nature of this enigmatic signal. So we are left with a fundamental and thrilling question. Is this persistent glow from the heart of our galaxy the first indirect glimpse of dark matter, the long-sought smoke from its invisible fire? Or is it simply the combined hum of a vast population of mundane, though fascinating, stellar remnants that we have yet to fully catalogue? The answer hangs in the balance, a testament to the meticulous and often frustrating process of scientific discovery at the very edge of our knowledge. This profound uncertainty also invites a more speculative line of thought, one that connects back to the hidden architecture of reality. Could the properties of this annihilation signal, if it is indeed from dark matter, be influenced by the existence of extra-spatial dimensions? In certain theoretical models, the process of dark matter annihilation could be enhanced or altered if it occurs within a higher dimensional bulk. The specific energy spectrum of the gamma rays, or the rate at which they are produced, could carry subtle imprints of particles annihilating not just in our three-dimensional space, but into or through these compactified realms. The galactic center excess, therefore, might be more than just a potential dark matter detection. It could be a complex message, one that encodes information not only about the particle itself, but also about the true, multidimensional nature of the spacetime it inhabits. Now, let's step back and witness a miracle so grand it often escapes our notice, the universe's journey from stark, breathtaking simplicity to staggering, intricate complexity. Picture the cosmos in its infancy, a near-perfectly smooth and uniform soup of elementary particles, a state of profound order that was also, paradoxically, a state of incredibly low entropy. From that featureless beginning, against the relentless cosmic tide of increasing disorder, something remarkable happened. Galaxies spun into being, stars ignited and forged new elements, planets coalesced, and on at least one world, chemistry gave rise to biology, which eventually blossomed into conscious minds capable of gazing back at the universe and wondering how it all came to be. This is the riddle of emergence, the puzzle of how complex, organized structures can spontaneously arise from simple underlying rules. It's a story woven from the threads of self-organization, where parts come together to form a whole that is greater than their sum, non-linear dynamics, where small causes can have disproportionately large effects, and information theory, which sees the universe as processing and storing data. At its heart, this isn't a story that defies physics, but one that is deeply rooted in its laws, a narrative where complexity isn't an accident, but an inevitable outcome under the right conditions. As physicist Sean Carroll compellingly frames it, complexity emerges naturally under the right conditions, driven by energy flows and computational processes. Think of the universe not as a static museum, but as a dynamic, evolving system with a built-in bias. That bias is the second law of thermodynamics, which commands that the total entropy or disorder must always increase. But this drive toward disorder doesn't simply create a bland, featureless chaos. Instead, it can create intricate patterns and structures as a side effect. A flowing river driven by gravity doesn't just smoothly erode its bed, it carves out meandering oxbows and complex deltas. In the same way, the universe, as it expands and cools, provides a constant flow of energy from the initial fireball of the Big Bang to the nuclear furnaces of stars. This energy flow acts as a kind of fuel, powering engines of complexity that can temporarily and locally build pockets of exquisite order, so long as they export disorder out into their surroundings. Your own body is a perfect example. You maintain your intricate, low-entropy structure by consuming energy from food and dissipating waste heat into the environment, increasing the universe's overall disorder even as you preserve your own local order. This process is fundamentally computational. The universe is running a program where matter and energy, following simple physical laws, process information and build complex structures over deep time. So, what are the specific mechanisms that transformed a smooth, hot plasma into the rich tapestry we see today? The primary architect on the largest scales is undoubtedly gravity. In the initially almost uniform universe, tiny quantum fluctuations were stretched to cosmic proportions during inflation. These minuscule overdensities acted as gravitational seeds. Over billions of years, gravity relentlessly amplified these small differences, pulling matter into vast filamentary webs. Gas collected in these dark matter halos, condensed and ignited into the first stars. This was the first great phase transition in the emergence of complexity, moving the cosmos from a simple, diffuse gas to a state with distinct, structured objects. Inside these stellar forges, a second crucial mechanism took over: nuclear fusion. The simple elements of hydrogen and helium were cooked into a dazzling array of heavier atoms: carbon, oxygen, iron, and all the elements of the periodic table. This chemical evolution vastly increased the universe's toolkit. Without these heavy elements, forged in stellar cores and scattered across space by supernova explosions, the universe would be a boring place, incapable of forming rocky planets, complex molecules, or life itself. The dust from dead stars literally became the building blocks for future complexity. Then, on at least one such rocky planet, a third and even more powerful engine of emergence kicked in: Darwinian natural selection. Here, the information processing of the universe took a dramatic leap forward. Through the simple, algorithmic process of variation, inheritance, and selection, self-replicating molecules eventually gave rise to the breathtaking biodiversity of Earth. This is a form of complexity that is not just structural, but functional and informational. Life is a system that not only processes energy, but also stores and transmits information across generations, adapting and becoming ever more complex in its responses to the environment. From this perspective, the universe seems to have a kind of preference for structures that can efficiently compute and manage information. A star is a simple information processor, balancing gravity and pressure. A bacterium is a vastly more complex one, with genetic code and metabolic networks. A human brain, with its trillions of neural connections, is perhaps the most complex information processing system we know, capable of creating art, science, and contemplating its own origins. The emergence of consciousness represents a pinnacle, a point where the universe became aware of itself. The journey of cosmic evolution is marked by these dramatic phase transitions, moments where the entire character of the system changes. The condensation of gas into stars, the formation of the first self-replicating molecule, the Cambrian explosion of multicellular life, each of these represents a threshold where new levels of complexity and new emergent properties suddenly became possible. This progression raises a profound point about fine-tuning. For complexity to emerge and persist, the universe's physical constants had to be set within a very narrow range. If the force of gravity were significantly stronger, the universe would have collapsed before stars could form. If weaker, no structures would have coalesced. If the nuclear forces were slightly different, stars might not produce carbon, the essential backbone of life as we know it. The universe appears to be finely tuned not just for existence, but for the emergence of ever greater complexity over time. This suggests that our ability to ask these questions is not a random fluke, but a consequence of a cosmos whose fundamental laws are inherently creative, allowing for a rich and open-ended future. So we are left to wonder, why did our universe take this particular path, transforming its initial simplicity into such a magnificent and layered reality? Could the potential for complexity be written into the very fabric of spacetime? This line of thought naturally pulls our imagination toward the possibility of other realms. If our universe is embedded within a higher dimensional bulk, as suggested by string theory, could these hidden dimensions influence the very laws that govern emergence? Perhaps in other pocket universes with different compactified dimensions, entirely different forms of complexity have arisen. Structures and systems of organization that are as alien to our understanding as a galaxy would be to a single-celled organism. The emergence of complexity in our own cosmic backyard may be just one single, beautiful example of a much broader, multidimensional principle of nature. Now let's stretch the rules of reality to their absolute limit. Imagine a particle that doesn't just push the boundaries of speed, but was born beyond them, a particle for which the speed of light is not a barrier but a minimum. This is the tantalizing and deeply problematic concept of the tachyon, a hypothetical entity that, by its very definition, would always and forever travel faster than light. Unlike any particle we know, a tachyon wouldn't need to be accelerated past light speed. It would simply exist in a state of perpetual superluminal motion, its very nature defying the cosmic speed limit that has defined physics for over a century. The idea emerged not from science fiction, but from a careful examination of the mathematics of Einstein's special relativity. The theory's famous equation doesn't explicitly forbid faster than light travel. It just states that as an object with real mass approaches the speed of light, its energy requirement skyrockets to infinity, making the feat impossible. But the equations hint at a strange loophole. If a particle were to always travel faster than light, its mass would have to be described by an imaginary number, the square root of a negative number, a concept that lives in the abstract realm of mathematics. This imaginary mass is the central enigma of tachyons, making them as much a philosophical puzzle as a physical one. As the physicist Gerald Feinberg, who coined the term tachyon from the Greek word for swift, wisely observed, tachyons are more than science fiction. They test the boundaries of what's possible in physics. They force us to ask whether the universe's rulebook is absolute, or if it contains chapters written in a language we have yet to fully decipher. If such particles were real, their implications would be nothing short of revolutionary. fundamentally challenging the bedrock principle of causality, the idea that cause must always precede effect. According to the logic of special relativity, if you could send a signal faster than light, there would always be some observer for whom that signal would appear to travel backward in time. Imagine a scenario where you use a tachyon beam to send a message to a distant star system. From the perspective of another spaceship moving at a high relative velocity, your message could arrive at its destination before you even sent it. This opens the door to the most mind-bending of paradoxes, like the famous grandfather paradox, where you could potentially send a message back in time to prevent your own grandfather from meeting your grandmother, thereby erasing your own existence and creating a logical inconsistency that the universe seems to abhor. The potential for such retrocausality is the primary reason most physicists are deeply skeptical of tachyons. Our entire understanding of the universe, from the motion of planets to the unfolding of history, is built on the unshakable foundation that the past is fixed and the future is open. Tachyons threaten to unravel that tapestry, suggesting that the arrow of time might not be a fundamental law, but merely a persistent local illusion. The fact that we have never observed a single instance of an effect preceding its cause in the natural world is a powerful argument that if tachyons exist, they must be somehow incapable of transmitting the kind of coherent, usable information that would allow us to rewrite history. The story of tachyons, however, takes a fascinating turn when we move from the realm of speculative particles to a more established role within quantum field theory. Here, the term tachyon doesn't refer to a particle zipping through space faster than light, but rather to a specific mathematical signal of instability within a field. When the equations describing a quantum field suggest the existence of a particle with an imaginary mass, it's not telling us to look for a superluminal messenger. Instead, it's a red flag indicating that the field is in an unstable, high-energy state, like a pencil balanced perfectly on its tip. This configuration is precarious and cannot last. The field will inevitably roll down its energy hill to settle into a stable, lower-energy state, a process known as tachyon condensation. This phenomenon is not just a theoretical curiosity. It's a crucial mechanism in the Higgs mechanism, which gives other particles their mass. In the early hot universe, the Higgs field was in a symmetrical high-energy state. The tachyonic instability of that field triggered a phase transition, causing it to condense into its current, stable state and, in the process, breaking the symmetry between forces and endowing particles with mass. So, in this context, tachyons are not physical particles to be detected, but mathematical harbingers of cosmic change, the instigators of the phase transitions that shaped the fundamental forces of our universe. This concept of instability and condensation finds an even richer home in string theory, where tachyons appear in the spectrum of certain unstable versions of the theory. In these specific configurations, the presence of a tachyon indicates that the particular vacuum state of the universe is unstable and will decay. The theory describes a process of tachyon condensation, where this unstable state collapses and rearranges itself, potentially settling into a new, stable vacuum with no tachyons present, a universe with stable physics like our own. This provides a compelling, if highly abstract, perspective. Our entire cosmos, with its stable particles and well-defined laws, might be the end product of a primordial tachyon condensation event, a frozen-in remnant of a more chaotic, unstable past. This transforms the tachyon from a potential particle into a fundamental actor in the drama of cosmic stability, a key that helps explain why our universe has the durable properties it does. Given the profound implications, scientists have naturally wondered how one might actually detect a tachyon, if it indeed exists as a real particle traveling through space. One of the most promising proposed methods involves a phenomenon analogous to Cherenkov radiation. When a charged particle travels through a medium like water faster than the speed of light in that medium, it produces a characteristic blue glow, a sonic boom for light. By the same logic, if a charged tachyon were to travel through a vacuum faster than the universal speed limit, it should theoretically lose energy by emitting a similar kind of radiation, even in empty space. This tachyon-Cherenkov radiation would have a unique and unmistakable energy signature. For decades, physicists have scrutinized cosmic ray data and the results from particle accelerators, searching for any anomalous energy loss or unexpected radiation that could be the fingerprint of a superluminal particle passing through our detectors. Despite these meticulous searches, no credible evidence has ever been found. The persistent silence of these experiments strongly suggests that if tachyons are out there, they either do not interact with ordinary matter in a way we can measure, or they simply do not exist as detectable particles within our stable cosmic framework. So, after this journey through the world of the superluminal, we are left facing a fundamental question that straddles the line between mathematics and reality. Are tachyons nothing more than useful mathematical artifacts, clever phantoms in our equations that signal instability and guide our understanding of phase transitions, but have no independent existence in the physical world? Or could they be real physical entities that are simply hidden from our current methods of perception? This line of thinking inevitably draws our curiosity toward the hidden architecture of spacetime. Could the paradoxes that make tachyons so problematic in our four-dimensional spacetime simply vanish in a higher dimensional context? In theories with extra-spatial dimensions, the geometry of reality is far more complex. What we perceive as a straight line in 3 dimensions might be a curve or a shortcut through a higher dimensional bulk. In such a cosmos, superluminal motion might not require violating local causality at all. A particle could appear to move faster than light from our limited perspective by taking a shortcut through a compactified extra dimension, much like an ant crossing a folded piece of paper by traversing the fold rather than walking the long way across the surface. In this breathtaking scenario, the tachyon's greatest theoretical hurdle, its defiance of causality, might be an illusion born of our incomplete dimensional view. The true nature of superluminal motion may not be about breaking the rules, but about understanding that the board on which the game is played has more squares than we can see. Imagine holding a credit card in your hand, its shiny surface catching the light. On that flat, two-dimensional strip, a vast amount of information is stored in a microscopic pattern, enough to recreate a perfect, three-dimensional image when illuminated with a laser. This is the magic of a hologram, where a lower dimensional surface holds all the data needed to project a seemingly solid reality. Now, take that concept and expand it to the grandest scale imaginable. What if our entire universe, with its swirling galaxies, swirling planets, and the very space you occupy, is itself a holographic projection? This is not science fiction. It is the radical proposal of the holographic principle, a revolutionary idea that suggests all the information contained within any volume of space can be completely and perfectly encoded on its boundary, a surface with one less dimension. At its heart, this principle forces us to confront a staggering possibility. The rich, three-dimensional reality we experience every day might be a magnificent illusion, a cosmic projection from a vast, two-dimensional screen at the edge of the observable universe. The seeds of this mind-bending concept were planted in the fiery debates surrounding black holes. In the 1970s, physicist Jacob Bekenstein made a profound discovery. He realized that a black hole's entropy, a measure of its hidden information or disorder, is not proportional to its volume, as one might intuitively expect, but to the surface area of its event horizon. This was a monumental clue. In everyday systems, entropy increases with volume. The more space you have, the more ways you can arrange the stuff inside it. But a black hole, the most entropic object conceivable, defied this rule. Its information capacity was fundamentally linked to its surface. Stephen Hawking later showed that black holes evaporate over time, and this created a terrifying paradox. If a black hole vanishes, what happens to all the information about the stars, gas, and matter that fell into it? Does it just disappear, violating a core tenet of quantum mechanics? This information loss paradox set the stage for a deeper insight. If the information isn't lost inside the volume, perhaps it was never truly inside to begin with. Perhaps it was always stored like a cosmic hologram on the event horizon's surface. This line of thinking was championed by physicists Gerard T. Hooft and Leonard Susskind, who formalized the holographic principle. Susskind, in particular, has become one of its most eloquent advocates, stating that the universe might be a hologram, with reality projecting from a lower dimensional surface. The principle draws its most powerful support from a mathematical framework known as the anti-de Sitter/conformal field theory correspondence, or AD-S/CFT. This is a concrete realization of the holographic idea within string theory. It posits a perfect one-to-one duality between a gravitational theory operating in a hypothetical universe with a certain shape, an anti-de Sitter space, and a quantum field theory that lives on its boundary, a universe with one less spatial dimension. In this breathtaking correspondence, the messy, complicated physics of gravity in the bulk of space is exactly equivalent to the well-understood, non-gravitational quantum physics on the boundary. A black hole in the higher dimensional space is mathematically identical to a hot, dense soup of particles on the lower dimensional surface. This isn't just a vague analogy. It's a precise dictionary that translates phenomena from one description to the other, providing a powerful tool to solve problems in quantum gravity that were previously intractable. The implications of this principle ripple out to touch one of the most perplexing modern puzzles in black hole physics, the firewall paradox. Imagine an astronaut falling freely toward a black hole's event horizon. According to Einstein's principle of equivalence, they should feel nothing special as they cross that invisible boundary. Space-time should seem smooth and continuous. However, quantum mechanics suggests that for an outside observer, all the information about the astronaut is encoded on the horizon. To preserve that information as the black hole evaporates, the horizon might need to be a searingly hot wall of energy, a firewall that would instantly incinerate the astronaut. The holographic principle offers a potential way out of this paradox. If the astronaut and the information they carry are fundamentally the same thing, described in two different languages, one inside the volume and one on the surface, then there may be no contradiction. The information doesn't fall in and get burned up. It is transferred and encoded onto the boundary, resolving the conflict by changing our fundamental understanding of where and what reality is. But how could we ever test such an abstract and profound idea? Directly observing the holographic nature of our universe seems impossible, but scientists have devised incredibly clever analog experiments. One promising avenue involves using tabletop systems that simulate the physics of black holes and event horizons. Certain exotic states of matter, like those found in superconductors or ultra-cold Bose-Einstein condensates, can be engineered to create an effective dumb hole, a point where sound waves cannot escape, creating an acoustic event horizon. By studying the quantum fluctuations and entanglement patterns in these analog systems, researchers can look for signatures that match the predictions of holographic models. For instance, the way information scrambles and thermalizes in a complex quantum system might follow the same rules as information falling onto a black hole horizon. These experiments are like building a small-scale model of the cosmos in a laboratory, allowing us to probe the fundamental rules of quantum gravity and holography in a controlled, observable setting, providing indirect but compelling evidence for this revolutionary view of reality. At the very core of the holographic principle lies the strange and powerful phenomenon of quantum entanglement. This spooky action at a distance, where particles remain connected regardless of the space between them, appears to be the glue that stitches together the holographic universe. The entanglement between different parts of the boundary surface is what generates the geometry and structure of the higher dimensional space it encodes. More entanglement between boundary points creates a shorter distance through the bulk. In this view, space itself is not a fundamental stage. It is an emergent property, a geometric manifestation of the complex web of quantum information and entanglement shared across the lower dimensional surface. The very fabric of space-time, the arena in which all physical events play out, may be woven from nothing more than these invisible quantum connections. This suggests that if we could somehow magically turn off all the entanglement on the boundary, the three-dimensional world we know would simply dissolve, vanishing like a dream upon waking. So we are left standing before the most profound question one can ask about the nature of existence. Is the solid, three-dimensional world we perceive the chair you sit on, the ground beneath your feet, the vast expanse of the cosmos, nothing more than a complex illusion, a holographic projection from a vast, two-dimensional surface at the edge of everything? The holographic principle forces us to consider that the true, fundamental workings of the universe are not happening in the volume we see, but on a distant, lower-dimensional screen where information is processed and stored. And this, in turn, weaves a final, elegant thread into our exploration of hidden dimensions. The holographic principle and the idea of extraspatial dimensions are not competing ideas, but are deeply complementary. In the AD/CFT correspondence, the higher dimensional, bulk space that contains gravity has more dimensions than the boundary theory. Our three-dimensional world could be the holographic projection of a two-dimensional boundary, but that entire system could itself be embedded within an even higher dimensional reality, as suggested by string theory. The hidden dimensions provide the mathematical room for the holographic duality to operate, creating a layered reality where our perceived world is both an illusion and a gateway to a deeper, more complex cosmic architecture. The holographic principle, therefore, does not just solve a technical problem in physics. It invites us to completely reimagine the nature of reality, suggesting that the universe is fundamentally an information processing system, and that we and everything we know are part of its magnificent projected display.